Good morning. Do you guys hear okay? I'm going to start us up. First of all, I just want to welcome you, and I want to thank each one of you personally. We invited you here, and you came. Some of you came a long ways, some from just around the corner. But the important thing is we're here together. We've assembled an amazing group of people for this workshop. I mean, you guys are world experts, scientists, engineers, politicians, policy people, resource managers, companies, mining, oil and gas industry. We've just got a tremendous gamut of people here that all can play a niche in the future of geologic hydrogen, and all who are, in my opinion, explorers in this new field. And why is this new field important? We know it's important because we need to make an energy transition on a massive scale globally. But in the Arctic, we need it for a lot of other reasons as well. We need it for our communities. We need it for our industry. It's a part of a strategic vision of what the Arctic can be. And that's exciting in Alaska. Yet, very little work's been done up here, quite honestly. We're at the beginning stages. So this is our opportunity to learn from you, who are ahead of us in many ways, and learn how this effort can be synergistic with other efforts and how we can all work together. And this workshop's a little bit different. We have over 100 experts here, but we're going to ask all of you to chip in. We're going to be doing a lot of exercises at the tables, believe it or not, to get so that everyone has a chance to put input in and everyone gets to see how their input is affecting the outcomes. Part of that is to develop partnerships, not prescriptive partnerships, but opportunities for you guys to work together, and particularly if it can relate to what we can do in the Arctic. So we're very excited to have you here. We're focusing on geologic hydrogen. We recognize it's only part of the picture, but with other forms of hydrogen, there are huge synergies in what we learn from each other. We want to make sure that as we map out geological hydrogen, we map to the other efforts, and other efforts map to what we learn here. So again, building an inclusive approach on the hydrogen ecosystem. Secretary of Energy likes to talk about this hydrogen being the Swiss Army knife, being such a utilitarian, broad-based, and flexible tool. It's a great analog. I would say geologic hydrogen is more like the Leatherman. It has the pliers that can really leverage those things where a Swiss Army knife can't necessarily by itself. So I see two tools in the toolbox: the Swiss Army knife and the multi-tool in doing that. The flexibility, sort of in that same metaphor. So we will discuss other forms on day 3 a little bit, and those potential synergies, looking at transportation and other issues. So we're trying to take a very broad view. We have a very broad group of folks here today, so that's really important. It's really important to recognize, as I talk, our sponsors. So we've had 3 major sponsors. One is the Arctic Research Commission. The second is the University of Alaska Fairbanks, and both the Office of Vice Chancellor and the Geophysical Institute, both funded and provide a tremendous amount of support to us here. And the third is the State Department Office of Arctic Affairs. Ambassador Sfraga is sitting down here, a former commissioner with the Arctic Research Commission, but he leveled up and is now with the State Department. So we have 3 great sponsors. But as important as the sponsors are the individuals that helped us organize this meeting. And I'd just like to call out some of those and like them to stand up if they would, and stay standing until everyone's recognized. It took a lot of people to put this together, and particularly on the short time frame that we have. So I'll start with the Geophysical Institute, Director Bob McCoy. I think Bob's here, would stand up. Then we have Associate Director Jessica Larson. Jessica. And Steve Masterman, who is the Deputy Director for Alaska Critical Minerals. Communications Coordinator Sarah Wilbur. Sarah, there it is. And Communications Manager Kelly Egan. Kelly here. Oh, okay. And Associate Director for Communications Becky Lindsay. And then we have the Office of the Vice Chancellor of Research, Vice Chancellor Nettie Labelle-Hamer. Executive Director of Operations, Sarah Fisher. Sarah here. Nice. Sarah Fisher Gold, I'm sorry. Forgot the hyphenated part. Senior Advisor, Brittany Smart. Okay. Communications and Public Outreach Coordinator Ulana Greenwell, who I think is out front, registering. Research Development Officer Helen Berman and Helen, and Assistant Administrator Carson Corner. And then finally, Suchi Marinas, a student support who's out in front doing the tables. At the USGS, research scientist and lead researcher for geological hydrogen, Geoff Ellis. DOE Arctic Energy Office, hydrogen advisor Paul McKinley. Paul. Senior Energy Advisor Levi Kirshner. Probably be here later. And then Director of the Office, Aaron Whitney, Dr. Aaron Whitney. And next, I'd like to recognize the Arctic Research Commission folks that really put a lot of work into this. Executive Director, Dr. John Farrow. Administrator Officer, Deborah Dixon, who's on a plane home due to a death in the family, but she did a tremendous job for us. Science Associate, Dr. Hajira Schmidt. Hajira. And also in his previous role, former chair and the current U.S. Ambassador for Arctic, Dr. Mark Sfraga. And just a few more folks that really bounced ideas, helped us support bringing the right people to this meeting at the right time. And that is the president of Alaska Marine Power, David Clark. And Dr. Mark Ivey, now retired from Sandia, who was one of our earliest supporters and brainstormers. And then finally, the last person I'd like to thank is Barb Bickford, sitting over here. Barb is a hydrogeologist who's now a reformed communications person who helps build meetings, helps coordinate, and she's developed the fabulous exercises that we're going to be doing together and lead us into a somewhat atraditional workshop, I would say. And I'm very anxious to see how it works out, but it will allow us to really work together, learn from each other, and all contribute. So I'm really excited about what's going to happen and Barb's hard work on this conference. Thank you. And with that, I'll turn it over to Barb to talk about the kind of the framework we're going to use in addition to the talks.
What? Good morning, everyone. That's better. Raise your hand if you've ever been to a conference where you walked in knowing nobody. A few people. Have you ever been to a conference where you sat in long rows and listened to talk after talk after talk and had, you wanted to talk to people, but you never had a chance? Yeah, me too. And at the end of the conference, you really didn't meet the person you finally realized was there, but they're already gone. Yeah. Okay. We are not going to do that today or this week. Okay. Is this the right one? Wrong presentation. Thank you. I'll just keep going. Who am I? Mark already introduced me. I am a hydrogeologist. I am also a former state regulator, and I'm an entrepreneur, and I'm a facilitator, meeting facilitator. I help scientists contribute their deep knowledge to the practical problems of our day, which is one of the ones that we're working on today. Now, a typical conference is, I need a picture. Well, you've all experienced it. Imagine, the rows and rows and rows of people and people up on a stage and they talk one by one. I hate that. It's boring to me. I get really tired of listening. So I'm always looking for ways to improve and innovate about meetings. We are here. You're good. You're going good. We are here. I'll keep going. We're here to collaborate. We are here to help shape recommendations for Arctic research of geologic hydrogen. We are here to contribute If you could run to this slide that has contribute. Yeah, keep going. There we are. We're here to contribute. We all have something to add, even if you know nothing about geology or nothing about geologic hydrogen. You can ask the innocent questions that need to be answered. You can also call us on using jargon. Those of us who are geologists, we love our jargon. So if you don't understand a term, ask your neighbors, ask the speaker. We are also here to connect. Many of you mentioned in your registration form that you really want to connect with people who are working on this issue, and we will do that. We will spend a significant chunk of time this morning, almost an hour, getting to know people at our tables and at neighboring tables. We will be able then to collaborate and connect more and contribute more. So we have some other ways we encourage you to connect. One is to use the message board. It's back there by the door that you came in. There's one message there now. Please populate it. We have structured discussions, as Mark mentioned. We have these table assignments. The first 2 days, you have an assigned table. There's the tables, as you probably have discovered, have diverse groups of people at them, of very different fields at each table. So we get different viewpoints. We also, you can have informal discussions about the stand by the posters or over by the rocks or based on what's on your name tag. And also, of course, around the refreshments. And there's more ways we'll connect. Overall, it's going to be interactive and informal, but we will also respect time. So first of all, before we go into our roundtable introductions, I want to share the 4 freedoms. You have freedom to speak up. You have the right to ask questions about anything that puzzles you. You can share your opinions and reaction, even your personal reactions, like, I really hate that. And you can talk about the freedom or the lack of it that you have. So if you feel like your voice is being suppressed, speak up about that. And finally, we have 2 ground rules. One is that we keep confidential, and I don't mean we're talking about your personal problems. I mean just the personal details and opinions that are shared here should stay here. The facts, the great ideas, they can go. It's wonderful. And then the other one is that we start and end all sessions on time. The reason we do that is we have a very ambitious but doable schedule if we stay on time. We don't want to shortchange anyone. We don't want, so please be on time when it comes to coming back to sessions. And also we've asked each of the speakers to speak no more than 10 minutes so that we can just keep moving. In many ways, I think you're going to find that you may feel we're rushed or that we didn't get enough time to talk about that point. The thing is, it's more of a taster. We're getting a sense of the big picture of geologic hydrogen. And then on the 3rd day, we'll dive into details. Okay. So I'm going to ask you if you agree to those 4 freedoms, and they're on there's sheets on the table. It's you can pass them around. Each person should have a sheet that says 4 freedoms on the top. We'll be using those in this next part. If you agree to do your best, you know, you may not do it perfectly, and there's going to be no freedom police here. If you agree, and if you're able, please stand. Come on, get your body moving. And if you don't agree, come talk to me, and we'll find a way to make sure it works. Okay? Thank you. You can sit down again. Now, roundtable introductions. Here's how we're going to do it. Let me get the first question we're going to ask. This is just a quote. It's about creating an atmosphere that we can really, really work together in. So the first question, it's on your sheet. How did I get here? You can say, I came up the highway on my Subaru. Or you came because you were invited by Mark or Geoff or somebody else. You came just because you're interested in this. Or your company has some kind of project on the side and you want to learn more. You have the freedom to answer that question any way you want to, but keep it to 2 sentences. Notice I didn't give you much space. And then the next one, the previous one was past focus. This one is more future focus. What do I want to have happen? You already answered this on your registration form, but maybe your answer has changed. And not everybody knows what you wrote in your registration form. So here's your opportunity to share that. You might want to meet people, learn about certain aspect of geologic hydrogen. You might want to solve things. You might want to make connections. And finally, what experience do you have that others could find useful? And it could be from your work. It could be hobbies. Maybe you grow up in a family of plumbers and you really understand fluid dynamics. Who knows, right? And relationships that you have that might be useful to other people. So you can get ready to share those. Okay, now I'm going to give you 5 minutes to think about your answers. Try to condense it down to 2 sentences for each answer. And then at the end of that, we will take the next step. So 5 minutes. Are we all done now? Are we done enough? Okay. Okay, wait. Still can't do this. There's a way we're going to do this. Here are some guidelines for sharing your answers. You have 90 seconds. We need to do this quickly. You have, for the whole table, you have less than 15 minutes to introduce yourself. So each get 90 seconds. And your table guides, who are the table guides? The ones that are, okay. Each table has someone who is kind of in the know on this. Yeah, thank you. They will, wait a minute. I want you to share your answers, even if they're similar to other people. And the point is, we want to know where the similarities are. Who's working on the same things or has the same questions. And if you're going to be leaving early, mention that in case somebody wants to connect with you. They know to meet with you today or perhaps tomorrow. And then if someone says, I need help with, finding people, investors, let's just say, I need help in finding investors. And if you know somebody who might be willing to do that, simply raise your hand and say your name. And that person will write down your name and you will connect later. Don't discuss, how you can help each other in this point, because we, again, have to stay on time, 90 seconds each person. And feel free to take notes. You can do that on the back of your sheet. It's or wherever you keep notes. Now, before I go on, I need to turn over my page so I know where I am. I want to make sure there's no wrong answers to these questions. Anything you say is a right answer. So I'm going to give you an example, my own introduction. I'm Barb Bickford. You heard that already. I'm here because Mark Myers invited me to help with this workshop. At first, he said it was going to be a one-day strategy meeting, and then it turned into this. I'm here to help you connect, and what I want to have happen is that you all find and meet the people that you need to move forward. That's my goal. And my personal goal is to see Northern Lights, although I'm not sure it's going to happen. The experience I have that I want to share is that I really enjoy meeting people from other cultures. And so, especially if you're from another country, please come talk to me. I've been a host mother to 7 international students. My daughter has been an exchange student to Japan, and I also lived in a house with international students in grad school. How long was that? Was that 90 seconds? It was less, right? So, and I answered more than 3 things on one question. I'm sorry, the 5 minutes is up. Okay, so your table will select a timekeeper who will give you a 15-second fair warning if you're rambling on a little bit. And you don't have to finish mid-sentence, but if you can, keep within the 90 seconds time limit. I will end the roundtable by ringing a chime. It's down there. And what time is it now? Is there a clock in this room? I probably can't see it. It's 8:56. Okay, so add 16 minutes to that. At 9:17. 9:17, this is going to end. Go. When you hear that sound, please go to silence. Now, you probably noticed at the bottom of your sheet, there's a little a reference to ally matching. We're going to do that right now. An ally is someone who you're going to be connected with for the rest of this conference, and you're going to help one another out. This is especially to welcome people who are here alone, who don't know anybody. So, here's how we'll do it. Let's see. If you are from Alaska, please stand. If you're from Alaska. Okay. And raise your hand. Stand and raise your hand. The rest of you, find somebody with a raised hand and pair up with them. Now we can mingle around. Go anywhere if you want. Okay? So if you're not from Alaska, find someone who's from Alaska and pair up with them. And bring your sheet with you. Can be anyone, anywhere in the whole room. What? Once you have a pair, kind of hold each other's hands up so we know that everyone's paired. Oh, I know. Well, everyone's not standing. If you have a pair, hold each other's hands up. You're paired? Okay. Please sit down. Please sit down. Please sit down and be quiet. Please sit down and be quiet. Who does not have a partner, an ally? So we have, okay, you two can be partners, okay? Anyone else who does not have an ally? Okay. Sorry, this was a little clunky. In a moment, I'm going to ask you to stand up and meet with your ally for 5 minutes and share the answers to your 3 questions. So you get to know your ally a little bit. And then especially, I want you to ask your ally, who is it that would be someone they really, really would like to talk to, either a person's name or a type of person. And you write that down on your sheet, and the rest of this conference, you're going to be looking out for each other, not only for your what you're looking for, but for what your ally is looking for. At the end of 5 minutes, I'm going to ring this again, and then I'll tell you the next thing to do. But you can go anywhere in the room. I know it's a little noisy in the front, so you can go in the back. 5 minutes, talk to your ally, share the answers to your questions. Go. Okay, wrap it up now. All right, folks. You have plenty of time to talk more at the breaks. Raise your hand if you have a really good idea of what your ally needs. Really good. If you don't, you need to talk to your ally more. If you know what your ally needs, raise your hand. Okay, you need to talk to your allies more. But we're going to move on to another round of roundtable introductions, and here's how we're going to do it. It'll be the same format, but what I would like you to do is get up and move to another table and sit somewhere, but not with your ally. So this is designed to help you meet 7 more people. So get up and move to a table, and we'll do another round of those introductions of 90 seconds each. No, any other table. You can go to any other table right now. Those of you who are still standing, please sit at a table and meet other people in a round table introduction, just like we did the first time. Any table. You have 15 minutes to complete your table. Can I have your attention, please? Can I have attention? Just 2 quick announcements, and then we're going to go to a break. Well, 3. Mark Myers. Mark Myers. Mark, could you come up here just for a second? Now, I have a question. Who here does not have an ally yet? If you came in late and you didn't get an ally, please meet with me up here at the podium just for a minute, and then we're going to go to break. Secondly, after the break, I want you to return to the tables that is the first number on your name tag, so that you are back at your original tables that's on the name tag. Even if there's just a few people at that table, we want you to go back to your original tables. And then, so Mark, wherever you are, everyone else, go to break. Do you want a 15-minute or a 20-minute? Do you want to start 15 minutes? So we're going to come back at 5 minutes to 10, 9:55. So we're going to be 5 minutes ahead, which saves like more time for questions, right? See you at 5 minutes to 10.
So we have a short 15-minute session, but this is an important one, actually. We're going to hear from real experts. You guys hear me okay? Yeah. Okay, how about now? Is that better? Yes, so we have 3 speakers lined up, and we have about 15 minutes, actually 4, and I'll introduce them, and they will really help set the stage, I think, for the importance of the work we're going to do in this meeting. So I'll start with our recording of Senator Lisa Murkowski. Many of you who know, but Senator Murkowski, in my mind, is just world-class in her integrity, the approaches she uses. When you meet with her and you have an issue, you better know your facts, because she will have read all the background material herself. She will understand all that background material, and she will ask you the tough questions. And so she's a leader in the Senate, and she's a leader for Alaska, and really cares about what happens up here. So we'll let her describe what she thinks about geological hydrogen in 3 minutes here. So can you roll the tape? The tape, that's antiquated. Yeah, how do you top that? Well, we'll ask our new ambassador at large for the Arctic to speak next, Mike Sfraga, who formerly was one of our commissioners with the Research Arctic Commissioner and chair, and was very supportive of this effort. Mike's also was the first formed the Arctic initiative at the Wilson Center. He, in that, looked at all Arctic issues, including energy, and liked to talk about the 7 Cs of the Arctic. So when we're thinking about the Cs of the Arctic, first of all, we have 4 Cs, 7 in the total Arctic, but in Alaska we have the Beaufort, the Chukchi, the Bering, and the North Pacific. So those are our 4 Cs. We also have 4 Cs connected with hydrogen, and maybe even 5. The first is communities. We can supply communities with energy. The second is commerce. We can create liquid fuels. We can aircraft fuels. We can fuel electric cars. We can do so many things on the commerce side. The commodities, it itself is a valuable commodity, but also a commodity that empowers us to develop other commodities in a more environmental sustainably way. And then finally, the big C is it improves climate, and it improves the decrease of decarbonization. So that's sort of 2 C's in 1, carbon and climate. So it's hard to find a single resource that could have such a big impact on our world in a way of helping our energy transition to move forward. And in the Arctic, we just can't do everything with electricity. We need these other sources, and we need the energy where the demand is going to be. And geologic hydrogen was likely to be distributed in areas that typically don't have fossil fuels. So the implications for us in the Arctic are huge. So with that, I'll bring up our Arctic ambassador, Dr. Michael Sfraga.
Good morning, everyone. First of all, it's nice to be back home in Fairbanks. Thank you for all of those who are not from Fairbanks to coming to my hometown to have this really important discussion. Mark referenced the 7 Cs. Now, for those of you who have heard me speak before about the Arctic, you may know about the 7 Cs, but it's the way in which I think about the North and how I think about Alaska fitting into the North and the broader Arctic, not just the state of Alaska, although I want to focus on the state for a little bit. But first, let me thank Mark Myers, we're commissioners together, for driving this issue with the U.S. Arctic Research Commission. The commission advances a number of priorities, and then the federal agencies bring those into their strategies as appropriate and as applicable. But the commission also looks for the seams, and maybe in this case it's both literal and figurative, but it looks for the seams. What are we not concentrating on? What's out there that a research commission should be looking at? What's important to our nation? What's important to the rest of the globe? What's important to the Arctic? Mark brought forward this idea, which, to be honest with you, I had never heard of before, right? Geologic hydrogen. I just stared at him. I don't know what that means. It sounds important, Mark. Explain this to me, which he did, and to the rest of the commissioners. And that's why a lot of you are here today, reaching out to Steve, reaching out to Geoff, trying to understand better what geologic hydrogen is for policymakers, but also what possibilities are there for the Arctic, for Alaska, and really for the globe. So that's a great role for the commission, a good role for the Department of State in this new role as Ambassador for Arctic Affairs, is to look at areas that fit our national strategy for the Arctic region. One of them is sustainable economic development. Another one is looking at the environment and climate. Another one is our nation's security. And the last one is international cooperation and governance. Well, energy cuts through all of those 4 really well. It also cuts through the 7 Cs, which I'll explain in a second. And I won't take much of your time this morning. But to me, there are 7 key drivers changing the Arctic, which really is changing the globe. And so the Cs is, trying to get your attention by saying 7 Cs, but they're not those Cs. They are what I consider to be the 7 drivers of change. One is climate. And so here we have this extraordinary possibility and opportunity with geologic hydrogen to mitigate, to think about different ways in terms of addressing the energy equation for the globe, specifically here for Alaska and the Arctic, and particularly for the North American Arctic. The second C is commerce, as Mark described. That's everything from shipping to really trade and thinking about energy's equation in that formula. The next is commerce and commodities. So energy is a commodity. The fourth is connectivity. And it's internet, it's reliable, affordable, redundant internet, but it's also ports and interconnectedness of our communities. And it's development of resources, which means that you have to have affordable energy. The fifth is the communities, and that's who ultimately we serve, is our communities, whether it's in the North or elsewhere. The sixth one is cooperation. And I think that just by a show of who's here today, including our colleagues from overseas, that no nation can do things alone anymore. You have to have international cooperation. And the seventh, sadly, is competition. And that plays out in a number of different ways. And as we've seen with the war on Ukraine, the energy equation has rippled across the world. So in order for all of you experts to consider this new possibility and this new opportunity, it's really important for all of us, but it also is a different way of thinking. We never quite looked for this before, the way in which you may help us look for this resource. We've never had, at least in my lifetime, a tectonic possibility of change in the energy equation for all of us. This is really important. And so in my new world of trying to both project, reflect our U.S. Arctic policy, but also informing, influence, and leading Arctic policy for the Department of State, Energy filters through everything that me and my new staff have addressed. Yes, there's some of the 7 Cs, but in meeting with allies and friends in the Arctic and outside of the Arctic, energy comes up in almost every discussion. And so that's why this is really important. And for my home state here, this is fundamentally important. It's important for the state's future. It's important for the Arctic's future. It's important for this community's future because we, as you know better than I do, energy is the key driver of everything that happens. So I want to thank you all for taking the time to participate. I will be in and out listening. I already have staff back in DC asking how this is going, and I have colleagues within the State Department who are very interested in this. So thank you all for coming. I'll look forward to speaking with all of you. And Mark, congratulations for pulling together what is long overdue. And thank you for opening our eyes to the potential and the possibilities and bringing together great people to try to make great change. Thank you.
Well, first of all, there's a lot of people in this room who deserve credit for bringing this forward. You know, I allude to this being taking a battery and jump starting a big semi truck. You know, we're just starting the engine. This is the truck. We're the people, and the people in this room are world leaders on the subject, or can be world leaders if they choose to be. So it's an exciting time. And with that, I'd like to introduce our last speaker for the session. I may end up with a few remarks as well, but it's Dr. Nancy Sun, who's the associate director, assistant director for Arctic in the White House Office of Science and Technology Policy. And I'd like to also, before Nancy comes up, acknowledge Dr. Larry Hinsman, who's sitting there, and please stand up, Larry. Larry's the previous director and a UAF leader. And Nancy's voice here is really important because it represents the White House's scientific view of all issues and helps coordinate federal efforts on Arctic science. Thank you.
Thank you, Mark. And I just want to thank the Research Commission and the University of Alaska Fairbanks for putting this workshop together. I'm delighted to be invited. When I received the invitation, I thought, I've got to be there, got to be in the room for this. So thank you. And Mark mentioned what I do. I'm in the White House, the Office of Science and Technology Policy. And one of the things I manage is it's an acronym, IARPC, the Interagency Arctic Research Policy Committee. Now that sounds really bureaucratic, and I suppose it is. But what we do is we bring together 18 federal agencies, offices, and departments around this topic of what is the national research agenda for the Arctic. And we have an Arctic research plan that we're now halfway through that my colleague Larry in the room, where were you, Larry? I'm trying to fill Larry's big shoes. They're bigger all the time as I'm discovering just how amazing this plan is that we're in. And I can tell you one of the things that's actually not in the plan, though, is geologic hydrogen. And so my presence here is I'm here to learn. That's what I put on my name tag because I think this needs to be in our plan in the future to think about this. And as I've only been in this role for a couple months, but two of the things that have been impressed upon me in those couple months, one is that the research that we do really has to benefit people ultimately. So I'm always being asked by my colleagues, what's the outcome here? Not just the outputs that we have a whole bunch of meetings and conversations and workshops, but what is the outcome for people? And I think the outcome here, if this works, if the geologic hydrogen turns into the kind of, if it has the kind of potential for the energy transition that we think it might, the impacts for people are clear. The other thing that's been impressed upon me is the importance of working together, not just federal agencies in their silos, each doing what they do, but really communicating with one another, communicating together early in a process so that we can bring all the expertises to bear that are around this room. And that's something that's hard. It requires time, energy. You all have day jobs that don't involve sitting in this room. But just this morning, the connections I heard around our table, it's amazing to me who is assembled here. And I wanted to just close with an illustration from somebody named John Hopfield, who I don't know if anybody here in the room knows who John Hopfield is, but he was one of the recipients of the Nobel Prize for Physics just this month. And I had the privilege of working on a committee with John like 25 years ago when he was a pioneer of bringing theoretical physics into biology, envisioning that there's a lot that could arise from that. And at the time, people thought, don't waste your life, going into biology, you're a physicist. But he really thought it was important and pursued it. And now he has a Nobel Prize to validate those efforts. And one of the things John said early on as I was just learning about that field was that when you want to create something new, you really start with a foundation of all these individual disciplines. It's like the bottom of a pyramid, and you're building a pyramid of excellence over that, resting on that foundation. And then what you have is something new that didn't exist before. And that really stuck with me, and that image popped back into my head as I was listening to the conversation this morning. That's what we're doing. So thank you, Mark. Thank you to the organizers for creating the conditions where we might create something new here that's never happened before. So thank you for that, and I'm eager to continue learning for the next 2 days.
So I'll just close this session out with just a couple of minutes of comments. Hopefully this is going to be fun for you. It's fun for me. I mean, think about what we're looking at. We're going from the top of the mantle to the top of the atmosphere to understand the system, first of all. So the integration of science that we need to do this is just phenomenal, right? The engineering we need to understand it, the measurements we need to take. We need to fundamentally look at a hydrogen cycle the same way we look at the carbon cycle, in a sense, to really understand the system. And then we have to figure out how to harness this energy, how to find it, how to harness it, and then ultimately how to scale it. So these are immense questions out there. But it starts with that fundamental question of how is the hydrogen being created, how much of it's preserved, how much of it is trapped, what fundamental science gaps do we have and how to understand it. And I can say right away from a resource potential, you have to be as smart in mining and in ultramafics as you are in conventional reservoirs, traps, and seals. And that in itself brings a different team together. The remote sensing we need is very difficult to sense hydrogen, as we know. The soil sampling testing aren't that great right now. We don't have really good ways to sense seeps. You look at the whole scale. We have to build a new structure for doing this kind of science. And we have to have teams, whether it be in the private sector, whether it be in the government, that are fully integrated and much broader in the sense than we traditionally had in any energy supply we've looked at before. So the challenge is great, but it's going to be fun, I think. I mean, you're on the edge of discovery. You guys are all explorers in this room, where you wouldn't be here. You all have an expertise and a super important role to play. So as we go forward, I think together this is going to be an exciting workshop. So thank you.
Well, good morning, everybody. And I'd like to welcome you all on behalf of the university to the university's Trothieta campus, which is here in the heart of Alaska, on the ancestral lands of the Dana people of the lower Tanana River. So welcome all, and really glad to have you here. I do have to say, though, that I have reached out to Senator Murkowski's writer who wrote those remarks, and to educate him on the definition of the word expert, because I am no expert on geologic hydrogen. I'm just happy to be here and help coordinate the meeting today. So I do have a couple of announcements. Firstly, for the presenters to avoid using a laser pointer. We do have some folks in the audience for whom that could be a considerable problem, so please no laser pointers. And then today, after the sessions here are over, Dr. Geoff Ellis of the USGS is going to be giving his distinguished lecturer presentation in the Wood Center pub, which is just downstairs, where we can all enjoy a cold malty beverage, and they do have food for sale down there as well. And then one final announcement is, I have to read this off my phone because somebody said it far more eloquently than I could say it. If we do have any journalists in the room, and I believe there are representatives of the press here, thank you for being here. We encourage you to connect with anyone you might be quoting to ensure you have a good understanding of the subject and what they actually said. And our experts who are here will be happy to help you. So as you can see, the agenda kind of travels through, turn my phone off, through the subject matter that we're going to explore today. And we kind of designed it to start with a general overview of geologic hydrogen systems, and then travel through Alaska's geology to see how Alaska's geology relates to what we know about geologic hydrogen systems. And then a smattering of research before we get into the policy and regulation discussions to close out the sessions. And one of the things you'll note on here is there is no session looking at the relationship of geologic hydrogen in the cryosphere. And so that's an area of research that we couldn't pull together because we couldn't find anybody to speak on it because nobody's looking at it. And so for the Arctic and for Alaska in particular, that's an area of research that obviously needs further attention because nobody's working on it. So I think with that, I'm going to pass it back over to Barb and Elena, because we skipped a Slido test. And so we're going to have a little Slido test before we get into the first presenters. So, Elena?
Good morning, everyone. I'm Elena Greenwell. I work here in communications in the Vice Chancellor for Research Office under Dr. Nettie Labelle-Hamer. And we've prepared the Slido, if you all are familiar as avid conference goers. So this is kind of an interactive aspect of the conference for a way for us to get feedback from you about what you're experiencing, what information you have to share, and some data points for it. So throughout the speaker sessions and just after, we'll be listing some questions on the screen. You can join from your phone by scanning a QR code that will show up when we click present, or going to slido.com. You'll enter in the code that's listed on the screen, and then you'll be able to answer some questions, respond to our polls. You'll see two small tabs at the bottom, polls and Q&A. So if you have any general questions, you can submit those to the Q&A and they'll be answered throughout the conference. And then the polls that will be listed will be specific questions. So first question will be, what is the primary question you've brought to this workshop? As that's open, feel free to answer. You can answer more than once, and throughout the conference, we'll address those comments. Thank you. It'll be shown.
I just want to add that some of the questions you can't answer more than once. So if you have more than one answer, we have 3x5 cards on the table. Also, if you don't have a phone or laptop, you can submit the answers to questions, not the Q&As, because the Q&As have to go to the moderator. But yeah, they're in your boxes. You can just type in there. If you don't mind, put the session number. So it says session 1. We're in session 1. So put session 1 and your key finding or your question. And at the end of the session, the table guides or who is ever in charge of your table will put them in the out envelope. All right.
All right. We're finally actually ready to get to the meat of the matter here. So if I could ask the presenters for the first session to come up to the stage here, and Nettie as well, who is our moderator, that would be great. So just for the Slido, also I think it's in the binder on your table, there is an agenda which has the Slido code and the little thing that you need to scan there, the QR code, and it's got the number in there. So, okay, our first session is basically the big picture look at geologic hydrogen systems. And our moderator is Dr. Nettie Labelle-Hamer, standing right here. Nettie is the current Vice Chancellor for Research at the University of Alaska Fairbanks. She got her doctorate in space physics. And after a stint in private industry, she became the director of the Alaska Satellite Facility. And from there, went on to be the deputy director of the Geophysical Institute, and now is serving in her current role as the Vice Chancellor for Research at the University of Alaska Fairbanks. And Nettie has been a great supporter of this meeting, and without her, it would not have taken place. So thank you, Nettie.
All right, thank you, Steve. So as you heard from my introduction, I am not a geologist. I don't know very much about this topic that it hasn't been told to me by someone in this room. People in this room are my source of information. So I really appreciate bringing together group of experts and people who are curious and willing to talk about things that are on the edge of things. So I appreciate this very much. It's my pleasure to introduce my esteemed colleagues. They are experts in this, so I look forward very much to their presentations. Geoff Ellis is a petroleum geochemist with the Energy Resources Program of USGS. His research interests encompass the areas of organic, inorganic interactions in petroleum systems, gas isotope geochemistry, and the controls on sedimentary organic geochemistry in aquatic environments. He's published extensively and has given many presentations, and we are very pleased to say that he will be here in our pub at 5:30 tonight. Everyone is invited to that. And I'm just going to give a little plug here. I'm not a beer drinker, but I can tell you that the Nanook Ale is, it helps our scholarship program. For every beer that you drink that is of that variety, $1 goes to scholarships for the students here at UAF. So drink what you want, but I will judge you if you don't have a Nanook beer. So, we look forward to hearing that tonight. I'm going to go ahead and introduce the whole group, and then that way we can just go into the talks. So Sarah is a geologist with the Central Energy Resource Science Center, specializing in basin modeling. Her expertise lies in the intersection of numerical modeling and geology. She's earned her BS from MIT in 2009, where her research focused on planetary geology. And her thesis investigated mantle convection models of Earth-like exosolar planets in tidally locked orbits. She received her MS from the University of Washington, Seattle, focusing on geochemistry and thermal evolution of large silicate. Yeah, did I mention I'm a space physicist? Magma reservoirs in the upper crust. She's then transitioned to the energy industry, working with upstream research company and exploration company at ExxonMobil, focusing still on the modeling, the thermal evolution of petroleum source rocks, as well as sedimentary basin analysis, fluid characteristics, I shouldn't read. Fluid characterization while drilling, and the role of naturally occurring CO2 and hydrocarbon accumulations. You can see immediately why Sarah is sitting on the front stage next to Geoff. Next to her, we have Greeshma Gadikota, and I want you to be especially sweet to Greeshma. This is her first trip to Alaska. There might have been a little bit of nervousness about coming to Fairbanks, and I told her, it's fine. It's probably going to be warm. There might not even be snow. Lies. So Greeshma is an assistant professor at Cornell University. Came in last night. She's in the School of Civil and Environmental Engineering in the College of Engineering, where she directs the Sustainable Energy and Resource Recovery Group. One thread of her research involves using X-ray scattering, tomography, and Why? She uses like super fancy techniques for observing chemical reactions as they happen. So between the three of them, it's a well-orchestrated walk through the systems. And so we're going to start with Geoff, and questions, I think that they can go to Slido. Is that right? So the Slido should be activated. If you have trouble with the Slido, Elena here will help you, but it's a great tool for us to make sure your questions get answered. Okay, thank you.
Thank you, Nettie. And thank you all for making the effort to get up here and turn out for this workshop. I'm really excited to be here. I've been working on this subject for 5 years now, and initially I was kind of alone in the wilderness with a small group of people looking into this, and the interest has just taken off exponentially in the last year or two. And so it's great to see this kind of event and the level of interest and enthusiasm for the subject. And before we get into too much of the geology and geochemistry and so forth around geologic hydrogen, I want to give us a little bit of a context for why we're doing this and what is the scale of what we're talking about here today. And so this histogram here is from a IEA study looking at their roadmap for how to get to net zero. And it's in that they talk about how there's going to be a need for hydrogen to decarbonize certain sectors of the economy that we just can't simply electrify with renewables. And so we're going to need hydrogen, and they predict that the demand for hydrogen is going to grow probably more than fourfold. Today we make about 100 million megatons of hydrogen from fossil fuels, and it's going to exceed probably 400 megatons per year by the year 2050. And it's thought that most of that was going to have to come from a combination of blue and green hydrogen made from fossil fuels coupled with carbon capture and storage, or from electrolysis of water using renewable electricity. And if we look at the amount of natural hydrogen that's generated annually, there's estimates that it's about 23 megatons per year for the entire globe. And so if we put that in the context of this 400 megatons per year, that would account for less than 5%, or maybe about 5% of what we think the annual demand is going to be, which would seem to suggest that this really isn't something that is worth thinking about or working on. But we have to keep in mind that the resource potential is not just dependent on how much is generated annually every year, but in fact, how much might actually get trapped in the subsurface, how long it could be held there, and could we actually successfully find it and produce it. And so in order to get some sense of what that endowment might be in the Earth's subsurface, I put together a study with my colleague Sarah here to try and come up with some kind of models to estimate what the global endowment of natural hydrogen might be. And we don't have time to go through the details of it, but I will talk about it much more this evening. And the model is a fairly simple box model where we have the constraints of the inputs that we use the existing knowledge about the behavior of hydrogen in natural systems, and then we filled in the gaps using analogs from other things like petroleum or helium. And I'll just skip to the results here. We assume that this natural system has been in place for millions of years, and then we can calculate how much might be then now trapped in the subsurface. And the first thing to note here, this histogram here shows that result. This is in megatons of hydrogen, and then the distribution of the probabilities. And so note that there's a lot of uncertainty here. The range is anywhere from thousands to potentially billions of megatons of hydrogen in the subsurface, with a mean value on the order of maybe around 5 million megatons. But it's also very important to recognize that this is for the entire Earth's crust. And so almost certainly the vast majority of that is going to be inaccessible. It's going to be in accumulations that are just simply too deep or too far offshore or much too small that they could never economically be produced. But as a thought exercise, I said, well, what if there is 5 million megatons in the subsurface, and if we could find maybe 2% of that, that would represent 100,000 megatons, which would actually supply all of that 400 megatons per year for more than 200 years. And so to me, the takeaway from this is that the potential is there, that it's likely that there are large amounts of hydrogen in the subsurface. And so the question is not, is it down there, but is it in places where we can find it and produce it? And so we need to understand what are the processes that could lead to accumulations of natural hydrogen, and how could we actually find them? And that's what we're here to talk about in this workshop in the next couple of days. There we go. And so we've been working now in the USGS on a project to try and get at this. And to do this, we need a geological framework to understand the potential to form accumulations of natural hydrogen. And we start with the well-established framework of the petroleum system, which is shown here. You have source rocks, you have migration pathways, reservoirs, traps, and seals. But we need to adapt this for hydrogen. So they're not going to be exactly analogous, the geologic features that come together, but the general framework can be applied here. And the other thing I'll note is that in petroleum world, we talk about critical elements that go into this petroleum system. But when I go out and talk to hard rock geologists or other people, and I mention critical elements, they think I'm talking about cobalt or lithium or something. And so we propose to call these essential components of the hydrogen system to be clear about this. And so there are some important differences and similarities between hydrogen and hydrocarbons. So one of the first key differences really is that the source rocks are very, very different. For petroleum, we're thinking about organic-rich sedimentary rocks, whereas hydrogen can be generated from iron-rich rocks or radiogenic sources or deep faults, and other mechanisms have been proposed. Hydrogen generation can also be much, much faster than hydrocarbons. Hydrocarbons take millions of years to generate from source rocks, whereas we can observe hydrogen being generated in nature in real time. Hydrogen is a much smaller molecule. The blue sphere there is a helium atom, and then we see the diatomic hydrogen molecule is about the same size, and then below that we see a methane molecule, a CH4. And so hydrogen is smaller than methane or any other hydrocarbons, so it makes it more diffusive, harder to trap. And there's important differences in the solubilities of hydrogen compared to methane or other hydrocarbons. And lastly, hydrogen is very, very reactive. There's a lot of inorganic reactions that consume hydrogen, as well as microbial processes that remove it. But there are also a lot of similarities to petroleum systems, where migration is largely driven by advective flow, and fluids follow the path of least resistance in the subsurface. Reservoir quality is fundamentally defined by porosity and permeability. These are things that we know very well from petroleum systems. Tracking mechanisms, timing and preservation. These are concepts that we work with in petroleum systems on a regular basis and have very good working knowledge of. Okay, so the other thing that to be mindful of is can we actually use one hydrogen system for all types of resources, of hydrogen resources that are potentially out there? And so the first concept for how we might produce natural hydrogen is where you have an external source of hydrogen. You have, say, water in contact with iron-rich rocks, shown in the center of this cartoon at the bottom. And that hydrogen is generated and migrates away from that source and gets up into a porous rock that has an effective seal on top of it and forms an accumulation. In that setting, we need all of these components of the hydrogen system: the source, migration pathways, traps, seals, so forth, in order to effectively have an accumulation. But it's been proposed that because the generation of hydrogen can be so rapid, it's possible that we might be able to actually produce it from the subsurface in real time as it's being generated, or maybe migrating away from that generation source. And in those settings, then we would really only need to know where the source rocks are and possibly the migration pathway in order to find that resource. And then lastly, it's been proposed that we might actually be able to stimulate these natural processes. There's a wide variety of ways that this could be done, but one simple process that might work is you could have iron-rich rocks that are in a setting where they are conducive to reducing water and generating hydrogen, but they simply don't have water moving through them. And so if we were to drill down and frack that and inject water, we could then make hydrogen. And so in that sort of environment, we really only need to know where the rocks are, and then we can just go in and engineer that. And it's important to recognize that that this global model that I showed you earlier with this potential for maybe 5 million megatons of hydrogen in the subsurface, that's only accounting for these natural accumulations. And so if we can actually get this natural generation or stimulated generation to work, that could actually even be substantially more resource. But we really just don't know how viable those are. That there's a lot of work that needs to be done there. So that's all I have for you. One more shameless plug for my talk tonight, where I can go into a lot more detail about all of this. And thank you very much.
Elena, can you go to the second to the last slide that she just showed? It's, I think, so we have some questions in Slido, but not that one, but the next one. I mean, there you go. So I think this is an important thing that we are looking at and looking at this week to see, okay, what is it, the things that we need? There are a couple of questions in Slido that we'll get to if we have time, but I do have one question that I would like each of our panelists to answer. And it's a little bit of a Russian roulette kind of game here. We're going to ask the question today, and we'll ask the same question on Wednesday after we've had a chance to, or excuse me, Thursday, when we have a chance to have the 3-day workshop. The question is, right now, with what you know, what's the probability of making an economic impact in 5 years with geologic hydrogen? You can use that one. Geoff, you're first. And there's no beer, so you have to just answer the question. No, it's not on. Here.
Okay. I'll preface this by saying that USGS management gets very upset when we speculate about things like what's going to happen in the future. So this is not an official statement from the U.S. Geological Survey. This is my own personal opinion. I think that there's a good probability, let's say better than 50-50, that there will be economic impact from geologic hydrogen within the next 5 years. We have exploration going on every continent. There's the latest number I heard is something like 70 startup companies that are engaged to various degrees involved in exploration. We've had more than a dozen exploration wells that have been drilled in the last couple of years. So I think that there's yeah, again, better than 50% probability that we will see some economic impact.
Yeah, thank you. And I just want to remind you what they said earlier about opinions need to stay here. Journalists, please be respectful. So yes, these are personal opinions. Sarah.
Yes, same disclaimer. I might offer a slightly more pessimistic view, which comes a little bit from watching oil and gas prospects get drilled from discovery through a development plan to production. And that takes some time. And so it's going to take some time to find successful ones. Now we're on our way, as you just pointed out. But once you find something, you have to decide how big it is and how to best optimize your production. And that's the development plan. And then once you start production, it takes a while before you actually start making money. That's the first time you actually have an opportunity to start bringing some dollars in. Up until then, you just spent money. And so 5 years is a tight timeline for that, in my opinion. But if you extended that timeline a little bit further, then I would be more optimistic.
And just a quick follow-on just for you is, what's the timeline for the Alaska maps that you were talking about?
Oh, the Alaska maps we'll probably have in we get in so much trouble for promising something. So
shorter than 5 years?
Shorter than 5 years,
okay.
Yes. We can say that.
Yeah. Greeshma?
I'll build on that perspective, and I'll say that in 5 years, we we're probably in a pretty good shape to have some pilot scale studies going on. Being able to stimulate the subsurface environment, being able to extract the hydrogen, figure out how we do the separation, figure out how we do the recycling loop of the fluid that we are recovering. I think all of that, in 5 years, if we can get some decent pilots going, I think we have a lot to learn then before we go to full scale production. And that would be in another 5 to 10 years. I can say that with, I would say, I'm being cautiously optimistic here.
Okay, thank you. And the reason why I chose 5 years is that it's been my experience when we're looking at new things in research and it gets out in the public that we are doing these kind of studies. The expectation and of a very fast turnaround is often a little overly optimistic for what's realistic in doing research development and then the exploration and the drilling, et cetera. So 5 years is fast. And I'm going to tell you the other side of that is if we are net zero by 2050, 5 years is slow for us to figure this out. So we are kind of in that space. I am going to go to Slido. Can I do that can I ask one Slido question? So, okay. To what extent is AI used for the mapping projections?
Well,
You go ahead.
So I think one of the considerations for AI is how you train your model. So in order to train a model, you're going to need both successful situations and failures so that the model knows when something doesn't work and when it does work. And we don't have a great data set for that. So in the US, the lower 48 has a fairly, what I'd say, like a nice data set of occurrences of hydrogen, and it is very small. So compared to other countries, it's actually a pretty good one, but it's actually very small. And the occurrences in which hydrogen is not is overwhelmed right now by oil and gas, which, as we've said, is maybe not even the right places to be looking. And so I don't think the training data set is robust enough to really help with machine learning just yet. But that's probably something that I think ARPA-E is active. The people are thinking about that. Smart minds are on it, but we don't have the training data right now to do it ourselves.
Okay, thank you. I think I would agree with that with my experience that we've done with machine learning and AI here at the university. It's all about the training data, and if you don't have the training data, humans are better. And I think that ends our session. So I'd like to thank the panelists again, and they're going to be here. Go ahead and keep going with the Slido questions because we will have an opportunity in some of the informal settings to have discussions about that. So thank you very much.
Thank you, Nettie and panelists. All right. Now we're going to spend some time interacting with each other and this material. But part of the way we're doing it, again, is the Slido. If you want to submit a Q&A, you still can. That will give us a sense of the kind of questions there are. But there's also the questions about, Elena, you want to put up the other questions now? There are some other questions we've just opened. No, not that one, the next one. Yeah, we could do this one. Do this one quick, if you can. Which sentence describes how much you know about geologic hydrogen? Let's see what the pulse is in the room. A lot of people don't know a lot about it. Yeah. And again, if you don't have access to a phone, you're always welcome to write on a 3x5 card, which are in the boxes on your table. Yeah. Okay. We have some smart people in here that could write a scholarly article about it. Well, I'll let you continue answering these questions. How does this work, Elena? Elena, how does this work? You open the next one then too? Okay. Okay, here's another question. So once you've answered the one before this one will appear on your screen. We have some optimistic people about Alaska. And we have some pessimistic people, unlikely. And the third question? What questions you have? Oh, we did that one already, right? Yeah. Yep. Session 1. Key findings. Okay. So I want you to know why we're asking these questions about key findings and the key questions and the research questions. Number one, the key findings will help the USARC when it writes its report about this meeting to know what to address in the report, you know, where to aim the, I guess, the audience. What's the audience? What questions or what key findings, what things that the audience finds most important, and that you are all the audience, but also the people who read the report are the audience. And then the next question, which is about research questions, not only will go into the USARC report, we'll also be compiling those and into themes on day 3. And we'll be creating research pathways. We'll form teams, little small groups, and we'll be forming research pathways for the most important questions. So all of you, by looking at the questions, submitting questions, we'll find out what are the most important research questions we think need to be dealt with for Alaska at this time, and we'll address them on day 3. So we're crowdsourcing that question.
All right, everybody, we're going to start the afternoon's session here. And this first session this afternoon, session 2, I believe, is on hydrogen systems or hydrogen generation. Yeah, geologic hydrogen generation. And as moderator for our session this afternoon, we have Dr. Jamey Jones of the USGS, and who's right here. And Jamey is the current Earth MRI project coordinator for the USGS, which is their flagship project on critical minerals. And Jamey's based here in Alaska at the USGS Science Center in Anchorage. His background is in bedrock geology, tectonic evolution, and mineral resources of Alaska. And it's been my pleasure to work with Jamey over the time I was state geologist as we were coordinating our relative activities in critical minerals. So it's a great pleasure that I introduced Jamey to moderate this next session. Jamey.
Thanks very much, Steve. And glad to be up here. It was a bit dicey getting out of Anchorage this morning. Got some a bit of snow overnight. Yeah, as Steve said, I'm Jamey. I run the USGS Earth Mapping Resources Initiative at present. For those of you who don't know what Earth MRI is, we are a national program that collects, that works with state geological surveys and collects framework geoscience data for primarily critical mineral resources right now. But of course, we're looking for overlaps with things like geothermal and of course hydrogen. That's why we're here today. So if you're interested in learning more about Earth MRI, please grab me and I'd be happy to chat more. But it's my pleasure to introduce our speakers for this session. I'm going to keep my introductions brief to let them tell their stories, and then we'll have some time for interaction afterwards. So first up, we'll have Monte Swan, who is the co-founder of the MagmaChem Research Institute. He's been funded by a host of mineral and oil and gas companies for more than 40 years, and he's going to talk about the geologic processes of serpentinization from source to seep, one way of generating geologic hydrogen. And Monte also has an excellent array of posters at the back of the room, so if you want to interact with him further, certainly you can catch him around the conference, but also check out the posters. Second, we'll have Ruta Karolyte, who is a postdoctoral researcher at Oxford, but I also saw a different affiliation on your slide, so you can explain more yourself. She specializes in noble gas signatures, fluid properties, and other characteristics of hydrogen and carbon dioxide systems. She's going to talk about the generation of hydrogen from uranium, thorium, and potassium bearing systems. And finally, we'll have Andrew Turner, who's a postdoc at the U.S. Geological Survey in Denver at the Central Energy Resources Science Center. Andrew is a stable isotope geochemist and works on formation and geochemistry of hydrogen. He's going to talk about the chemical and isotopic signatures of gases that are generated in these natural systems. So we'll start with Monte.
Thank you, Jamey. Let's see. Okay, thank you. Title of the talk is Geologic Hydrogen and the Process of Serpentinization. And to understand the geologic process, which is the gap that we've been talking about, I believe, this is geologic history of serpentinization, you need to understand some deep earth processes. And this is a petrotectonic model of a layered earth. And on the left column is the seismic section. The right column is a chemical, petrologic, radiometric model. And they were done independently and they match. So I think it's a pretty good possibility that the mantle has layers. And there's 8 layers, chemically distinct, physically immiscible. And these were generated from this classification, magma metal series classification, manganese rocks and mineral deposits. That led to the discovery of 20 deposits on 3 continents, worth about $103 billion, which was a pretty good economic proof of concept. So this is the basis for what we're talking about. One time I gave a paper at APG, annual conference in Denver. It was 2001, and Exxon Research came up to me afterwards, a group of them, and they asked me this question. When we do the accounting for supergiant oil and gas accumulations, the books don't balance. Do you have any idea what we're missing? And they went on to describe all these strange metals and oil that don't seem to belong there. And then they said there's too much hydrocarbon in the supergiant systems. Exxon Research actually said that to me. And then they said, we don't understand how plate tectonics relate to oil. We ended up with funding from DOE and Noble Energy, and innocently, I like to say, discovered serpentinization to answer all the questions and more. That started us on 20 years of serpentinite research from about 2001 to present. And much of that was with Statoil's New Ideas Group. And they actually started a company with us to apply this to oil exploration. And they're now named, changed the name to Equinor. So serpentinization is on the right, and the peridotites, which is a precursor to serpentinites, is on the left. There's xenolites up at the top. You've got olivine as the main mineral, and you have a group of serpentine minerals, chrysotile, lizardite, and antigerite, state mineral of California, actually. You get about 40% increase in the volume when you serpentinize, and you can see there's some hydrogen generated. So the source of the peridotites that make the serpentinite, that make the hydrogen, there's 2 sources in the mantle. There's a shallow source, they're Hershbergitic. I like to call them subalkaline. And their chemical profile is similar to type 1 oil brines. And then the other type, alkaline, they're lerzolytic, they're deeper in the mantle, and they're related to they're type 2. They have a chemical profile of type 2. And this is a spider diagram of the 2 types, 40 elements, and the pink is the deep ones, and it's much more crust-like in its chemistry. And the shallow ones are not as much. They're more depleted. I think they're depleted in those elements. And the deeper you go in the mantle, in the layers, the heavier the elements become. This is a little summary of it. And the shallow ones have actually higher hydrogen than the deep ones. And you got nickel vanadium ratios are higher, sodium potassium ratios are higher. So there's a difference, but they both produce hydrogen. The settings, out of the 5 major plate tectonic settings, 4 of them are obviously serpentinite settings: oceanic rifts, normal dip subduction, flat subduction, continental rifts. And all these words below, and you can see the details if you go up to my poster session. That's 193 case studies of serpentinization from 3.8 billion to present day. It goes through the whole geologic history. You have this same process going on. And Statoil named it ultra deep hydrothermal. We like to call it UDH systems. So this is one of the cross sections. As I said, you can see them back at the poster session. And I've got the equation for the hydrogen production of hydrogen at the bottom there. Hydrogen's in blue. Here's normal dip subduction, flat subduction. And there's 4 different places in the fractionation of the serpentinite brines that you produce hydrogen, which is really surprising. And here's the rift setting. This is taken after the North Sea, and that's pretty much what the seismic showed. The Moho, which we call the serpentosphere, comes right up within 2 kilometers of the base of the basin. You can see the hydrogen released. And here's just a cartoon. Hydrogen released during supercritical serpentinization, during dehydration of the serpentinite, which gives you a steatite, which is talc. And then during the crystallization of the brines, as you start going subcritical, which means you start becoming more ionic, you start breaking water down, and you create chemical muds like dolomite muds and quartz muds. And then up at hydrothermal dolomite, you release more hydrogen. So there's 4 places where you release it. Here's the equations for releasing it. And on the left is our classification and how we discovered all those mineral deposits. It's a 7-layered hierarchy. And it takes you right to a specific type, which you can tie economics to. Well, I did a preliminary one for hydrogen after all my research so far. And I think the first thing you do is look at what's the source, the type of mantle peridotite, and then what's the plate tectonic setting? What's the water source? Oxidation state is absolutely critical. You have to have reduced crust for hydrogen to be stable to make it anywhere near the surface. And then you have the serpentinization process, which is super critical, and then migration and deposition. You go through these and you can classify the occurrence of hydrogen and relate it to economics. This is how we do with mineral systems. Up on the left-hand side, there's 6,000 mineral districts we defined in the US. This is a geologic outline around the mineralization. So it's actually a rock unit. And in Arizona, we had 1,100. And this just to show you the details we have here. Each one of these are mineral systems, and they relate to the source layer in the mantle. And this is all empirical. This is not a hypothesis or theory or model. This is just straight empiricism. And these have names, and then they have the location, source, and then a date. And what that does, it ties the source to a time. So we have 32 time slices for the Western US. So we've actually mapped, and next one's Alaska. We can do this with Alaska. We started doing it with Southeast Alaska, started mapping the mineral systems. But those mineral systems and the igneous rocks, you can tie to the subduction zone. Whether there was one there, you can say whether there was one or there wasn't one there. But you end up with a topographic map, and that's what that is for that time slice, 89 to 72. And you see these tears. These are these faults. These are tears. These are subducted fracture zones where you have different buoyancies on each side. So when the oceanic crust goes down, it has to tear. And the panel of crust above each one of those is a geologic province. You can't go across those lines. They're about 300 miles on the average. They go all the way from Argentina all the way through Alaska. So to map those in Alaska, you have to map the mineral systems and igneous rocks and then classify them and tie them by the potassium content to the depth of the subduction zone. So this is fundamental to finding the height. And here's a thickness map of the crust, and you can see they match. I mean, you get decretion, tectonic erosion of the base of the crust when the subduction zone gets very flat. Here's another way to look at a stratotectonic section. You take the paddle of crust, project data to the common line, and you can map the chemical facies of the arc. That's the only way you can do this. And then you can tie all geology to it. All the geology in the panel of crust above the subduction zone ties directly to it as it steepens and flattens. And then oxidation state, absolutely critical. You can look at ferric ferrous ratios on igneous rocks because they buffered to the oxidation state of the crust. And where you have reduced crust, which is the cool colors there, you have gold, diamonds, and oil. Those are all stable when the basement is reduced. If it's oxidized, those are not stable. Actually, the gold goes into the magnetite because you get magnetite series igneous rocks. So this is really important for hydrogen. Without this, it's not going to make it to the surface. Another thing is serpentinite diapir it goes from apritite is non-magnetic and it's high gravity, like 3.6. Serpentinite is 2.6 and highly magnetic. So they stick out like a sore thumb. So you fuse the magnet gravity, which is it's a little tricky to do. You got to have a geophysicist set anyway, heard a ring. But this is a way to map the serpentinites in the basement. And then the conduits, I believe they have to be strike slip wrench faults because that's the only way to open up low pressure areas in the deep basement. And you also get the damage zones, which can be reservoirs in the basement. And how do you see them? Well, you get a reduced column of gas coming up of hydrogen, and it alters the surface oxidized material, which is usually down to about 1,000 feet. And you get like a zeolite here will become very, have high resistivity. So you can use TM or controlled source, and you can actually locate the seeps that way. So that's it.
Thank you very much. It's very stimulating. Terrible pun. Next up is Ruta to talk about uranium, thorium, and potassium bearing systems.
Very much for the introduction. Yeah, my name is Andrew Turner, and I work on natural hydrogen related projects, a couple of them at the USGS. And what I want to kind of go over today just quickly is sort of a preview of how you can use the chemical and isotopic signatures of gases from natural hydrogen systems in order to understand the mechanism of those systems. All right, so I'll just throw up this nice figure, which we've already seen today once, that really just gives a great overview, especially in sort of the lower portion there, of the kind of mechanisms of production that we have here with natural hydrogen. So there's sort of three main ones, and I have the blessing of going after people who just talked about both radiolysis and serpentinization, so I can kind of rely on that and not really discuss it very much at all, but mostly talk about how those appear in nature. And so at the bottom, number one there, we have basement rocks that are interacting with water, and this is the radiolysis reactions that we just heard about. And we have serpentinization-based reactions, number two there at the bottom, and then number three is sort of these more enigmatic potential primordial hydrogen from deep faulting. And so a central question, as these mechanisms produce hydrogen, a lot of that hydrogen is going to migrate upwards and end up potentially in traps where we might then access it from the surface. And if we're accessing hydrogen from some trap or reservoir, it may not be immediately obvious what mechanism produced the hydrogen that's there. And so a question is, how do we identify the origin of gases when we find them in nature? And so I'll just sort of walk through a kind of multi-step, almost holistic approach to trying to figure out what produced a gas. So the first one, and probably the most obvious one that I think everybody would think of, is doing abundance or simply concentration of different components of a particular gas. So there's a large number of potential sources of natural hydrogen, as I mentioned, and the hydrogen concentration on its own is not especially meaningful. I mean, it's nice if you find a place that's 90% hydrogen, but that doesn't really tell you a ton about what is producing that. And so, molecular composition of a particular gas, the percent hydrogen versus percent methane or percent nitrogen is really helpful in trying to diagnose what potential mechanisms could have produced that. So on the right, I have this nice ternary diagram from Prinshofer, where we have a handful of different places from ophiolites and other conventional systems, and they plot kind of all over the place. And even, similar systems plot in different places here. And so that sort of brings me to my next point, which is to say that this isn't always enough. It's a good place to start, and it's certainly very helpful to understand, what other gases are present alongside hydrogen, but it's not always enough. And so to go from there, I want to move into talking about isotopic compositions and how they can help. So this figure, I appreciate it looks a little complicated. Let's just break it down. I want to just focus very quickly on isotopic compositions and what they are. So this figure from Euler is sort of just a schematic showing, if you have some molecule, you can have a substitution of a different isotope. And for those who don't know, an isotope is the same element, but with a different number of neutrons. So in the case for hydrogen, instead of hydrogen, you have deuterium. Or for oxygen, you can have oxygen 18. And when you substitute one of those into the structure of a molecule, then that is a single substitution, and that's what we would consider sort of a bulk isotopic composition of something. So measuring that, we typically think of isotopic compositions in delta notation. What I want you to kind of take away from this is really that we're measuring the ratio of how much deuterium is in a sample relative to the normal hydrogen divided by some standard. So you can think of it as sort of normalized to something. And so I'll just show you some data that was compiled by Milkov in 2022. In particular, in this plot on the x-axis, we have the isotopic composition of molecular hydrogen from a handful of different places. A lot of serpentinization related systems and others, hydrothermal systems. So they've got some natural data in there. And what you can see immediately is that it spreads about 800 per mil or so, or even more, in terms of the delta D of this hydrogen. And so, you can start to put together a kind of different regions for crustal versus mantle primordial produced hydrogen. And you can just sort of do this empirically. But this isn't the end all be all. When you find something that looks like this in nature, it may not actually be because it was produced in some situation. In particular, the lower isotopic compositions, like in the -800 and 700s, there's multiple different ways you can do that. And for particular, those are low temperature equilibration with things like water can also move your isotopic composition in that direction. So it's definitely not, a definitive thing, just looking at delta D of H2 alone. And so unsurprisingly, I'm going to advocate for looking at more than just delta D of hydrogen. If you look at other molecules, in particular, like in this case on the right, they've added in the delta C13, so the carbon isotopic composition of methane. And then you can start to see, you have two different spheres that are sort of emerging here on some of these. So multiple species can help you determine the source of this hydrogen with a little bit more precision and confidence. And in particular, for the kind of talking about things like hydrogen, or of course hydrogen, methane, ethane, CO2, and even helium and others are useful things to be looking for. And as with hydrogen, consideration must be given to whether or not the source signal is what is being preserved, or if it's some overwritten signal from reequilibration later. So coming back to this diagram, I want to go even one step further and talk about clumped isotopes. This is a more novel technique looking at specifically two substitutions. So in the case of hydrogen, it's two deuteriums. I mean, it's a simple molecule. So it's literally two deuteriums together instead of two protium hydrogens together. And like in bulk isotopic compositions, we have this sort of ratio notation here. It's a little bit different, but the effect of the end product here is you have some measure that is actually that actually changes with temperature and has a very strong relationship with temperature. It doesn't always do that, but it has a very nice thermodynamic equilibrium that has this temperature sensitivity. And so you can see on the right here, these are from some experiments from Maginot, and what they did is a bunch of different temperatures, and you can see pretty strong changes in the order of a couple hundred per mil in the clumped isotopic composition. And this can actually be really helpful. It's another piece of information. If you go into the field and you make measurements not only of the bulk isotopic composition, but of the clumped isotopes, you can start to see, potentially the temperature at which something was formed or later re-equilibrated. Major caveat like before is it's unclear if this is reflective truly of the source conditions. This is something especially to keep in mind with hydrogen, in particular in cases where you have water around. And then, you can do clumped isotopes of methane. This is even a more mature, more mature set of science. And, this has been related to biogenic versus thermogenic determinations and higher and low temperature production. And so this is providing, potentially complementary information. And the key thing is that the rates of reaction for re-equilibration between methane and water versus hydrogen and water, these are different. So you can end up with a situation where if you have these gases together in a reservoir, you might have, your hydrogen isotopic signal may become overwritten over time, but the methane isotopic signal may retain the source signal. So I want to briefly then finish off with noble gases. And this complicated figure is really just to show you that, noble gases, as we just, especially helium, as we just heard before, they also are formed, through radiolysis or otherwise, and can migrate into these systems. And in particular, if you start looking at those in systems where you find helium, on the y-axis here, we have R over Ra, which is a common noble gas literature measure, which essentially is the ratio of helium isotopes in your sample versus that of atmosphere. And you can see there's a pretty broad spread on the y-axis, but there's also, if you cross-plot it versus the delta D again on the x-axis, you can, again, start breaking things out into these different groups. And none of this is foolproof, but it's another dimension for analysis. And these helium isotopes in particular can help pinpoint sort of the origin, whether or not it's crustal or potentially primordial helium on atmospheric origins. Now, there's always the potential that the hydrogen and helium are unrelated to some degree, and there's the potential for that in any of these gases, that you might be looking at something that has methane and hydrogen, but they may not have been formed in the same way. So what I essentially am advocating for is taking sort of a holistic look, non-uniquenesses in individual isotopic compositions, individual molecules, can be overcome by looking at multiple different ones together. And the chemical and isotopic compositions of these gases can tell you a lot about the mechanisms or potential mechanisms that produce them. But you have to take good care looking at these data and not, make it, you have to be careful with your interpretation. So yeah, with that, I'll finish.
Thank you very much to all three of our speakers, and certainly you'll hear more on these things later as we look at these processes and where they might be occurring or have occurred across Alaska. So Slido is pretty quiet right now, but there is a question that I think is worth investigating. Ruta, it's to you first. What time scale is radiolytic hydrogen generated on? And I've actually asked the same for serpentinization. I can see if it's on. Is there a on switch?
So yeah, I guess the question would be how long is enough to, accumulate radiolytic hydrogen? And that is a good question. That would depend on radiolimit concentrations. Some of the fluids have been observed naturally. They have fluid residence times over hundreds of millions of years. So for instance, that is a sort of scale. It's a very slow process. Something like tens of millions, I think, is enough to produce in the right areas enough hydrogen to form a gas phase. But certainly it is on a much slower end of generation relative to, say, serpentinization reactions. And that's why the environments are, again, quite different, where we're looking for these environments that are very quiescent and where the water is sort of very slow. The movement of this is very slow, and we can accumulate these gases for these periods of time.
I haven't really thought about this, but Serpentinization occurs all the way from 3.5 to the present. So the process has been going on, and it's controlled largely by plate tectonics. So I think, you know, you have continental breakup, and you have heat coming up from the initial rifting, and then you get serpentinization and steatization, and then you get magmatism. So there's a cycle there. Perhaps, well, let's see. Subduction, the cycle is probably 700,000 to 1.2 million. That's what we see in the stratigraphy. I don't know. I mean, I could just, it's kind of complicated because it occurs in all the plate tectonic settings in different ways. That's a good question.
Yeah, no, I was thinking the same thing. I mean, there is no answer, but if you're thinking about the ingredients that you need to make a system that could be productive, you know, time is obviously an important ingredient because in some cases we're talking geologic rates, especially when you're in a tectonic context. A question for Andrew, since that you were sort of excluded from that conversation. I think looking towards sort of discussions to come, do you have any sense of what isotopic signatures would be predicted for potential Alaska environments?
I will preface this by saying I know very little about Alaska in terms of the geology, and that's one of the things that I'm really excited to learn from this workshop is like a little bit about the kinds of rocks that are up here. And so I think I don't really have a good sense of what isotopic signatures you might see in Alaska. It would depend, you know, on which kind of systems you're looking at. So for radiolysis or for serpentinization or for potentially, you know, deep faulting, those can have somewhat distinct but also overlapping signals. And so I think it's really at some level quite specific to the particular situation, be it a reservoir or basin or otherwise. So yeah, sorry, I don't really have a satisfying answer to that. I'm not sure.
We had to put you on the spot anyway. I also like the question that just came in at the top. And so thinking about hydrogen as a potential resource and serpentinization versus radiolysis as being two of the methods for generating hydrogen, can you talk about I mean, it's again sort of that time scale, but also process scale question. What's the relative production of serpentinite versus the radiolysis systems in producing geologic hydrogen? I'll start over here.
Well, my first comment is paraluminous rocks generated during flat subduction. They can be very radiogenic. They're probably the most radioactive igneous rocks. In fact, that's what probably makes most of the roll front systems in the sedimentary, in the basins. So I would say, you have to think about the rate of paraluminous generation. I mean, this is plate scale, flat subduction, and you melt the base of the crust hydrously, and you produce these huge magmas that never make it to the surface because they're so full. They have 10 volume% water, so they crystallize at 8 to 12 kilometers. And when they're uplifted slowly, I think that's probably one of the primary sources for that. And now I lost track. What's the question? That's right. Oh, and serpentinization is in a lot of ways tied to this same. During flat subduction, you get serpentinization coming after the paraluminous production. As you cool down the flat subduction, then you start getting serpentinization. So they're just superimposed right on top of each other. It's impossible to answer a question like that.
It's impossible to answer, but it's fun to talk about, right? You have a comment?
Yes, I guess it sort of depending in what kind of frame we're asking that question, relative production, that is through serpentinization or radiolysis. So we have some estimates, for instance, for the continental crust globally, which is kind of a little bit back of an envelope, but it's assessing essentially the volumes of the different types of rocks in a continental crust, and then sort of some modeling about how to do with weathering and to do with uplift, how much rock we're getting through in geological periods of time to estimate kind of the rate of serpentinization as well as we can estimate the rate of radiolysis through radioactive decay. So basically, doing something like that, it's around 70% for serpentinization, 30% of radiolysis for sort of global production since Precambrian time. This is probably not exactly correct, and certainly in specific areas, if we're looking, at different kinds of rocks, some of them would do just serpentinization, some of them would just do radiolysis, depending on mineralogy and also depending on the age. Sometimes, most commonly, there will be a contribution of both these sources. As well as, I guess I would say that for serpentinization, there's so much potential of iron oxidation where, naturally the iron never gets oxidized for natural processes. And so if we're thinking about engineered hydrogen, then we can produce much more through serpentinization.
Yeah, thank you for that. One more question for Andrew. Can you talk about how microbes can affect the isotopic signatures of the gases?
Yes, this is a huge deal. Those of you who are familiar with isotopic compositions might sort of know that in a lot of cases, microbes tend to make very light isotopic materials. And so in the case particular of hydrogen and from methane as well, microbes do produce both hydrogen and methane that have quite light isotopic compositions. And in fact, a lot of times those overlap with the lower portions of, where I had the crustal or low temperature related isotopic composition. So determining the difference between microbes and processes that are happening in the crust, or re-equilibration in particular with water, is actually really difficult. And part of the way that you can try and get around that is with some of these clumped isotope methods. And the reason for that is just that the reactions are a little bit different in that the ending composition, when you have microbes doing something, they don't always end up the same way in clumped isotopes as they do in bulk isotopes. So in a place where you have overlap in the bulk isotopic composition, the clumped isotopic composition can look very different from equilibrium. And so that's one way to try and get at this, but it is sort of a difficult problem, in particular in soil gases, which is one of the things that I'm working on as well. Not the topic of this talk, but looking at the presence of hydrogen and methane in the soil gas and trying to use that for prospecting, that becomes really difficult to distinguish between biological and abiotic processes. So it's a really important thing that I think needs more study, but I think there are ways to sort of look at multiple different isotopic systems and then try and understand it from that perspective.
Yeah, thank you for that. It seems like we have about time for one more question, and there's a question that's specific to radiolysis that it's worth asking. How important is the back reaction of oxic products of radiolysis with generated hydrogen in radiogenic rocks? And I'm going to ask that to Ruta. How important is the back reaction of oxic products of radiolysis with generated hydrogen?
Oh, the back react. Oh, I guess this is about generating hydrogen, but then hydrogen again, sort of forming water with the oxygen. So yeah, like that certainly happens. So through radiolysis process, we create so many different super reactive radicals. And there's a series of different reactions where these compounds will form different compounds. And if there is a lot of oxygen in the water, hydrogen will recombine with some of the oxygen. So, but generally, sort of environments where the water is there's a lot of oxygen in it, generally are not going to be these environments where the water is very old and the hydrological system is very slow. So where we are able to preserve large amounts of hydrogen, generally it will be an anoxic sort of environment. And so essentially that calculation for kind of the production of hydrogen through some kind of energy output through decay will account for this of sort of the relative mass balance of forming different compounds, including sort of recombining with oxygen.
Yeah, thanks very much. And thanks for all the great questions and points of discussion. Can we get one more round of applause for our speakers? All right, well, that concludes the session on generation of hydrogen and gas compositions.
Okay, everybody, we're going to start moving into Alaska's geology and looking at how what we heard about hydrogen generation could fit into what we know about our state. And we have two sessions on that. And the first one really delves into the tectonics of our state and also into sort of the metamorphic, I guess, serpentinization of our state as well. So this session is going to be moderated by Dr. Michael West. And as we all know him, he's Mike West, but he asked to be referred to as Michael West. So I don't know what I'm doing here. Anyway, I know him as Mike, so I'm going to call him Mike. Mike directs the Alaska Earthquake Center and currently serves as Alaska State seismologist. And in this capacity, he oversees the state's earthquake monitoring. And for those of you who don't know, we have over 40,000 earthquakes a year, and Mike's organization monitors those. And with the USGS, DGGS, and Homeland Security, also produces tsunami mapping products for our coastal communities. And then most recently, the Alaska Earthquake Center is engaged with an interagency effort to identify, detect, and warn about significant landslides. So with that, Dr. West.
Okay, I'll try to be brief here and kick us off into our next section covering all things tectonic in Alaska. We've got a great lineup of speakers here. The first presentation is put together by Barrett Salisbury and Carl Tape. Barrett is with the State Geological and Geophysical Survey. He manages the program on earthquake and tsunamis there. I am fortunate to cross paths with him frequently in that role. He also is currently chairing the Alaska Seismic Hazard Safety Commission. And Barrett is a veritable Swiss Army knife of geologic hazards in Alaska. So whether it's landslides, tsunamis, earthquakes, if you're working in the geology and the landscapes of Alaska, you want Barrett in your Rolodex. So this talk is co-led or something with Carl Tape, who's sitting in the audience, who's a professor of seismology in the geosciences department here at UAF. He is an immensely talented and successful seismologist who I have the pleasure of working with. Perhaps most relevant to this group, however, over the last few years, Carl has helped spearhead the effort to develop an Earth System Science graduate level program, which has been really a monumental effort to try and break down some of the silos of that are sort of historical structures create in departments and enable more interdisciplinary, cross-disciplinary kinds of Earth systems research and education, recognizing that Earth science is a giant Venn diagram of overlapping systems. And I think that's particularly pertinent to the topic of geologic hydrogen, because that's probably one of the main programs where students in a geologic hydrogen future would be coming out of at UAF. So with that, I'll pass the mic over to Barrett.
Thank you very much, Mike. Appreciate the introduction. My name is Barrett Salisbury. As Mike mentioned, I'm the Earthquake and Tsunami Hazard Program Manager at DGGS just down the hill. I'm a paleoseismologist, so I'm going to talk about Alaska's current state of active tectonic deformation and crustal scale faults through that lens. And we'll start with ancient faults. We'll move into quaternary active faults, and then we'll talk about modern active faults. And I'm going to do my best not to blur those two last categories together too much, but I'm going to. So this map on the left shows a structural representation of the Cordilleran origin of Northwest America. And what this shows is several distinct terrains. And these terrains are blocks of geologic units that have distinct histories compared to their neighboring terrains. The big black lines are these major faults, or that's what it would lead you to believe. But one thing I want you to take away from this image is that not all of these major faults that are depicted here have lots and lots of relative displacement between it and its neighboring terrain. We know that in the intermontane terrain, the green one basically, including the Tanana uplands, that there are a lot of superposed fault displacements on old structures that have formed post-accretionary. And so the estimates of total slip along these faults have come down since the 90s. So it used to be over 2,000 kilometers of dextral slip that we attributed to some of these major faults. We now know that it's probably less than about 1,000 kilometers of displacement. But the take-home message here is that these faults shown here have evolved over time in relation to their neighboring terrains. And so not all of them are actually suture zones that were previous subduction zones. So keep that in mind. But what this does show is that the Queen Charlotte Fault, the Denali Fault, and the Kaltag-Tintina system still are the framework for the modern deformation we see in Alaska. And so we fast forward to today. This is 1 year's worth of earthquakes in Alaska from the Alaska Earthquake Center. There's about 45,000 events here, colored by depth. The maroons are deep, over 150 kilometers in the Earth's crust. And the red ones are shallow crustal earthquakes. The magnitude bins are 4 and 6, so we can see that we have more small earthquakes than we do the big ones. And what we can immediately see is that this is controlled by subduction of the Pacific plate beneath the North American plate. And that major pattern describes that behavior between the tectonic plate boundary. If we look in the interior, and I'm not able to point, but if you squint your eyes at the interior, you can kind of see the Denali Fault and the Kaltag and maybe the Tintina in interior Alaska. So that active seismicity helps us recognize where these active faults are occurring. And I want to emphasize that the Yakutat microplate plays a huge role in that. So otherwise, simple subduction is complicated by the impingement of that microplate on the North American plate. And that gives rise to a lot of the deformation we see in central Alaska. So the rotation of south central Alaska and extrusion to the southwest. As we move away from the plate boundary where the plate rates are shown, the Alaska Aleutian subduction zone, the Queen Charlotte Fairweather Fault both accommodate about the entire plate rate on those two individual faults. As we move farther north, the slip rates and strain rates decrease by orders of magnitude the farther away we are from that subduction zone. And so this is the first digital compilation of quaternary active faults in Alaska. This was from DGGS and Rich Kaler and others in 2012. Largely a compilation of existing faults from George Plafker that were discovered through mostly geologic studies and paleoseismologic studies. And so we can see in the background, we still have a tremendous amount of pre-quaternary faults that are mapped into bedrock. We include them here just to show you how complicated this terrain actually is and the assemblage of terrains actually is. And what we see are these colored lines that represent age of recent activity. And this was our first attempt at describing all the known faults that are busy in Alaska with relation to one another. And so in the last 1.6 million years, those colors represent their relative activity. And so for engineering geologic studies, earthquake faults that are in the latest Pleistocene and then the Holocene, so in the last 15,000 years, those are considered active faults that are candidates for future faults, or future earthquakes rather. And the red lines up there are the historic ones. So you see that we don't have a whole lot of classified active faults, even though we have a tremendous amount of deformation or potentially areas for deformation in Alaska. And part of the reason is the geologic conditions in Alaska are terrible for preserving surface deformation of these crustal faults. Not all faults are exposed at the surface, so many are blind, and not all fault ruptures are of magnitude 6 or greater, or 6.5 or greater, which is about the threshold where we expect there to be surface rupture with them. So we have a lot of faults up here, but we don't have a great geologic record of what's going on. And so that's when we turn to our modern techniques like modern seismicity and geodesy to assess where that strain is being released in the upper crust. And this is just another picture. It's a longer term assimilation of active tectonics in Alaska. But again, you can see some faults like the Denali and the Kaltag that are starting to show up a little bit better. And one other thing we can do with a modern strain rate field is make block models of how we think the upper crust is deforming across Alaska. So we have slip rates for the subduction zone. They're colored by different degrees of coupling between the overriding and the subducting plate, but we also have slip rates for these major block bounding faults. And we put these block bounding faults into these models in a simplified version. We know it's more complicated than this, but we have to start somewhere. One of the major benefits of this approach is that it gives us estimates for slip rates in places where we don't have any geologic observations, like the Caltag, where the slip rate's about 2 millimeters per year. We know that it's been active in the last 750,000 years, but otherwise we don't know how fast it's moving. So that's one real big benefit of the geodetic studies. And so to show you how much more complicated it can be than that geodetic block model, we've got that block model again shown in blue here. We're going to zoom in on the Denali Fault and look at all the different geologic studies. Those black dots are individual landforms that have been studied or paleoseismic trenches that estimate slip rates. The gray lines above the active fault are segment average slip rates. And in the very bottom of that, we can plot the slip rates along strike and compare them to what we see in GPS data or with other remote sensing studies like INSAR. And if you look at that one gray dot there below the red line and the black dots of the geologic studies, we see that the slip rates don't always match up. And it really depends on the time scale over which you're looking as to the slip rate you're going to get for a certain type of fault. And so that's another complicating factor that people deal with all over the world. We especially have that problem here. And so this is a summary figure. It's probably my favorite figure of the total behavior of South Central Alaska. We can see again that the Yakutat microplate is foremost front and center. The gray region is the subducted part of the Yakutat microplate. The big white arrows in the bottom, 53 and 50, they show the total plate rate as predicted by the geodetic models. The black arrow pointing to the north-northwest with up to 3 millimeters of year is the pole of south central rotation's indentation over time. So we are indenting. The white circles are the geologic estimated slip rates, and the white ovals with arrows are the geodetic predicted slip rates. And what this shows us is we have a very discrete pattern of indentation, rotation, and extrusion. So to the northeast across the eastern Denali Fault and the Wrangell-St. Elias, we have contraction and uplift. We have rotation of south central Alaska and extrusion to the southwest. We have contraction and uplift in the western Alaska range and across the northern foothills fold and thrust belt. In interior Alaska, we have these bookshelf left lateral seismic zones that accommodate that rotation. Caltag Fault and the Tintina in the north are still accommodating that right lateral deformation. And so if we have to simplify that, this is what we end up with. This is not a replacement of the Quaternary Fault and Fold database, but it's another type of database used for a different purpose, and this is for a seismic hazard model. And so one thing I want to point out is that those dashed faults like the Caltag, the Iditarod, Nixon Fork, they have really low nominal slip rates, but we know from modern seismicity and we know from geologic studies that we are undervaluing the slip in some of those places. We still have a lot of work to do in Alaska, but we're coming along pretty well. And our updated seismic hazard maps as of last year have really put some changes on what we know about seismic hazards in Alaska. I think that's my time. Yep.
All right, next up we have Jessica Larson. We've got significant time for questions toward the end of this session, so we'll save until then. But next up is Jessica Larson, who is a professor in the Geosciences Department here at UAF. She is also currently the Associate Director of the Geophysical Institute. Jess has her fingers in a lot of different things, but I'm gonna single out 2.5 decades, closing in on 3 with the Alaska Volcano Observatory. And in that role, she's spent a lot of time, a lot of professional time devoted to the problem of how gases and rock interact with one another. And while that's heavily in the volcanology world, I like to think there are some parallels to the geologic hydrogen topic of the day. I'll also point out, I've watched Jess, known Jess for a few decades and watched her in a lot of different settings, and she has a particularly strong grasp of how different agencies come together and work together on big problems. So academics plus state plus federal, these can be hard consortia to manage and navigate. And I've seen Jess in those settings, and she brings a particular expertise. So,
thank you, Mike. Okay, we're gonna take a little bit of a step back here, and we're gonna zoom out on plate tectonics after Barrett's really great talk here. I'm gonna just step it out a little bit, and where I'm gonna lead you in my 5 minutes is towards what Marisa Acosta is gonna talk about, which is serpentinization in modern subduction zones. So if we step way back out and kind of go back to Geology 101, the Earth is made up of rigid lithospheric plates, the tectonic plates. Mantle convection is releasing heat from the interior, and as part of that, it moves the plates relative to one another, which gives rise to the three primary plate tectonic boundaries. We have convergent boundaries at subduction zones, we have divergent boundaries at the spreading ridges and at rift valleys or mid-oceanic rifts. And then at transform boundaries, the plates move laterally past one another. So some of the crustal scale faults Barrett was talking about fit that bill, as does the San Andreas fault zone in California. In the North Pacific region, we're really rich in subduction zones. So dominated by subduction zones in the Pacific Northwest, US, that's Cascadia, Alaska, and the Aleutian Islands. We have our very own subduction zone here. It's kind of amazing for a state to have its very own ginormous subduction zone, in my opinion. I'm always very, very excited to be here for that. And then Kamchatka and Japan. So in these locations, the Pacific plate is sinking down into the mantle underneath more buoyant continental and oceanic lithosphere. So here's my much more simplified map of subduction, modern subduction in Alaska. If you want to talk about details, I'm happy to do that separately outside of this talk. As Barrett discussed, we have the Yakutat microplate or Yakutat block, which is subducting underneath kind of the mainland portion of Alaska towards the east, creating a lot of really interesting tectonic problems. Crustal extrusion goes out towards the west, towards the Bering plate. And then the Pacific plate is subducting underneath both the North American plate and then a somewhat recently resolved Bering plate that's rotating clockwise in the Bering Sea area. Oblique subduction in this area, I didn't put a lot of detail on this map, but the block model that was talked about in the previous talk actually extends out along the Aleutian arc as a series of rotating blocks due to that oblique subduction. So you get areas of relative compression and extension along these blocks as you head out towards the western Aleutians. We've seen this cartoon before, but I just wanted to note that this subduction zone, well, actually two if you count Yakutat, is the reason why we have one of the most seismically active regions on the planet. We have more earthquakes per day than anywhere else in the US, including California. So this is, again, that really nice 2023 seismicity compilation map from the Alaska Earthquake Center. We're also very volcanically rich. We're one of the most volcanically active regions on the planet. We have 54 historically active volcanoes in the state of Alaska, 1 to 3 ash-producing eruptions per year. Volcanic ash is the main hazard to aviation and people living downwind. It is a real hazard, even though most of our volcanoes are remote. Ash clouds can travel for thousands of kilometers downwind. We have tsunami hazards related to volcanic landslides, and we have more frequent eruptions and magma production than elsewhere in the US. So we're a very, very magmatically rich state. So what's going on inside the Earth to produce this rich array of geologic activity? And how does this link up with geologic hydrogen? So this is going to be the lead-in to what Marisa is going to talk about. This is a cross-section of kind of an average subduction zone where you have a downgoing subducting lithosphere. It brings in volatile rich sediments from the ocean floor. Those are driven down into the earth at that plate interface. A lot of those are scraped up and off into an area called an accretionary wedge or an accretionary prism. That's kind of at the forefront of where the subducting oceanic lithosphere meets the continental or overriding oceanic plate. And it's in this region where you get lots of big earthquakes. You also get serpentinization. That's where you can have the conditions that are right in this sort of slab
crust mantle interface area where rocks can serpentinize. Deeper down is where you get dehydration reactions on the top of the slab in hydrous minerals that are coming down in those subducted sediments. That water is released into the mantle where it basically lowers the melting point of the mantle peridotite and generates partial melts that percolate up into the crust and feed our active volcanoes. And with that, I'm going to turn it over to Marisa to go in even more detail.
All right. So next up, Marisa Acosta, who is a professor of economic geology here in the geosciences department. She's a high pressure, high temperature experimental geologist. She runs the economic geology lab here, which I don't think I need to state the relevance of that to today's topic. I'm going to single out, she's been at UAF for 10 months now. This is a new and exciting add to our research portfolio, and we are fortunate to have lured you to Team UAF.
Thank you. I'm fortunate to be at UAF. Okay, so today I will tell you a little bit about when serpentinization occurs in the downgoing slab. There are effectively two places where serpentinization occurs. It will occur right before the oceanic crust dives down into the subduction zone, and then again a little bit farther down when it dehydrates, as Jess mentions. So when it dehydrates at depth in the subduction zone, the fluids move upward into the mantle wedge and can also serpentinize the mantle wedge itself, which will generate abiotic hydrogen gas. Okay, so to serpentinize a downgoing slab prior to it entering the subduction zone, the slab must first be old enough and cold enough that it will crack when it bends to dive down. And so that means that it needs to be at least 10 to 15 million years old to be that old and to be that cold to develop these cracks. And these cracks can extend all the way down into the lithospheric mantle, and that will allow for ocean water to penetrate into the oceanic lithospheric mantle, and we can serpentinize it at that stage. So we get serpentinization of the mantle wedge before we even enter the subduction zone proper, because of these normal faults that form during the slabbing, the downgoing slab. I guess I'd talk for a little bit as a preface to my next slide about the different types of serpentine polymorphs. The mineralogists in the room will maybe appreciate the quotation marks because they are not proper polymorphs being related. They have these different structures. We have chrysotile, which is the lowest temperature, least stable polymorph, and tigerite, which is the medium temperature polymorph, and it has that sort of modular structure up above. And then we have lizardite, which is the intermediate polymorph, and it has these flat stages. Yeah, so all you need to know is that there are 3 different kinds of serpentine, and the relative proportions of each different kind vary depending on where in the earth you are looking at a piece of serpentinized rocks. And this has implications for the processes of serpentinization and deserpentinization in the subduction zone. So here is a diagram showing the relative distribution of serpentine polymorphs in the downgoing slab. So here we have serpentinization of the deep sea peridotite before it dives down into the subduction zone, and you develop a combination of lizardite and chrysotile, which are stable to about 400 degrees Celsius, at which point they will convert into antigerite, which is stable all the way down to 600 degrees Celsius. And when it hits 600 degrees Celsius, that's when it decomposes and releases all of the hydrogen and all of the water that's stored inside of it. So it gets down to 600 degrees Celsius in the subduction zone, breaks apart at exactly 600 degrees, fluids come off, and this produces forsterite, aqueous fluid, and enstatite, and earthquakes. That fluid then can migrate upwards and interact with the peridotite in the mantle wedge, where it will serpentinize it if it doesn't partially melt it. It depends on the structure of the temperature gradients in the mantle wedge, which one happens. So The fluids coming off the downgoing slab move vertically upward into the mantle wedge, where they melt and metasomatize or serpentinize the mantle wedge and generate abiotic geologic hydrogen, which is too deep for us to ever get to, I'd say, but interesting from a geological perspective. Yeah, so that's how basically we get serpentinized peridotite in subduction zones proper. That's it.
Okay, we have one more speaker in our session here. Next up is Elizabeth Nadine, who has broad expertise in tectonics and geology, real broad professional experience as well. She spent 13 years as a professor of geology here in the geosciences department. She's run field programs, mentored students, written extensively, both for professional audiences, but also for public audiences. I've had the pleasure of working closely with Elizabeth over the last year or so as she's managed communications at the Alaska Earthquake Center. I know she's talking on subduction zones today, but I would also point out that Elizabeth's career at the intersection of science and communications is particularly pertinent when trying to build large initiatives like the one we're discussing during this workshop, when trying to communicate, frankly, hard and new topics to public, media, legislature, regulatory bodies, et cetera. Folks like Elizabeth are good to have on your team.
Okay, thank you, Mike. I'm going to start by saying that I have violated one of the principal rules of public speaking. I've crammed 23 slides into a 10-minute segment, but I was charged with talking about the history of subduction in southern Alaska, which is a very big topic. So we'll get back to this picture in a minute, though, because it's really amazing. Where am I pointing this thing toward when I press play? Okay, so as Barrett kind of alluded to earlier, Alaska is built through accretion of several terrains over time. So they both talked about kind of modern history of Alaska. We're going to dive back to 250 million years and go forward. So Alaska is made of accreted terrains. Origins and boundaries are still being investigated. That's what makes science really exciting. The southern Alaska margin grew substantially in Mesozoic time. There were 3 major phases of magmatism and then deposition of marine sediments. There are actually still contrasting models of how a volcanic arc, which I'll talk about a little bit, was accreted. And then my work with my students really was looking at the tectonic development in southern Alaska. We did a lot of interpretation of databases. There's still a lot of data to be collected for southern Alaska and other parts of Alaska, mapping in accretionary prism rocks and fault rocks as well. So I don't know if you've seen this image before. Ray Troll, he talks about Alaska as the Great Alaska Terrain Wreck. That is basically Alaska. It's a collage. You could call it a patchwork quilt. Barrett showed this slide already. The one on the left, I've just removed the names of the terrains from it. The one on the right, I really just wanted to point out another thing that was spoken to was that there's a decent amount of Cenozoic cover. So exposure can be tricky, and that's actually what leads to a lot of opportunity as well, is like investigating what's under that cover and solving some of those outstanding mysteries. Okay, so the southern Alaska terrains, I've labeled the ones I'm going to talk about, mainly the peninsular terrain in that purplish, a little bit about Rangelia, and then Chugach to the south of it. So peninsular terrain is effectively a volcanic arc. You could think of the modern Aleutian Arc as the peninsular terrain. The fault that bounds it to the south, the Border Ranges Fault, is basically the subduction zone that we have Pacific North America subduction zone preserved. Rangelia composite terrain was 2 oceanic fragments that came together before they were accreted. And then south of peninsular terrain is the accretionary wedge that was accreted after the volcanic arc got put in place. So this is basically what that looks like, right? We've got a volcanic arc. This is how continents grow also. This thing, think that modern Aleutian arc, think of it just jammed into southern Alaska. And that's what happened starting about 250 million years ago. And the model basically looks like this, where there's a subduction zone. That the thing in the middle where it says migration of volcanic front is basically the Talkeetna arc. It got flipped on its side. So that we actually preserve both the moho and the mantle at Earth's surface, one of very few places in the world here in Alaska where we can walk from the continental crust into the mantle at Earth's surface. And then, as I mentioned, kind of behind it, there was a subduction zone. That one's preserved as the Border Ranges Fault. I should mention the subduction zone in front of it doesn't have a great preserved signature, and from what I understand is not at Earth's surface. So coming back to the title slide, this is Bernard Peak. It's a mountain across the road from Tonsina, Alaska. You can hike up here and you can hike into the mantle, which is pretty amazing. This volcanic arc is considered the world's premier example of a complete exposed arc sequence, which is really exciting to have here and accessible. So of course, because it's mantle rocks, there are also serpentinite. There is also serpentinite here. So these are some of my early graduate students. And really interestingly enough, it's highly serpentinized, but also still preserves mantle flow fabrics, which is pretty exciting. But you can see here that typical serpentinization of the peridotite in the area. So the cross-section has been pretty well worked out. It's on the left over here. We can consider kind of a stratigraphy of a volcanic arc. And starting at the bottom, you've got the mantle rocks, and then you move into garnet-bearing metaplutonics. There's gabbros and all that stuff. Lots of thermobarometry that's been done. As I mentioned, it kind of flipped on its side. The image to the lower right is that just kind of map section. So just note the north is to the right. And so you're looking at the deepest rocks on the left. The surface volcanics are on your right, and then you walk southward and you walk into the mantle. And then there's this big fault, and then you're in the accretionary prism of that subduction zone. So as I mentioned, in large part accreted terrains, and Barrett mentioned separated from each other by faults, not all really well exposed at the surface. Border Ranges Fault is a major tectonic boundary, and I kind of went out hunting for it. I thought I'd found it. It turns out, well, in this particular place, and it turns out it was a different fault altogether, but I'm going to talk about that a little bit. The model of how this arc was accreted, I mentioned, is still up in the air. Was it one arc? Was it two? Was part of it ocean, and part of it was ocean-continent? I think people are still talking about that, but we won't go into the details. So one of my students just assembled all of the published data and then added some data to try to answer that particular question. We need more targeted studies, and the geologic framework for understanding geologic hydrogen, I think, is going to be pretty important. Lots of geochemical data suggested there were different tectonic environments for different parts of that arc. And so we kind of agreed with this model of two subduction zones, one within the continent, one within the ocean, existing at the same time, and then juxtaposing those rocks. I mentioned I was interested in the Border Ranges Fault, so I ended up also in the accretionary prism, which is just south of that Border Ranges Fault. So I'm going to talk a little bit about that as well. In this particular area of the Matanuska Valley, there's some really spectacular rocks now exposed that weren't before because of glacial retreat, which is another Alaska phenomenon that is currently being studied. So we found these like crazy fault rocks. All of this is carbonaceous material, as it turns out. It turns out it wasn't the Border Ranges Fault. It was this big fault zone within the accretionary prism. But in discovering that, we were able to change the location of the Border Ranges Fault, which had been mapped in the 1970s, and that mapping propagated forward. And this is not uncommon in Alaska or really any other place. It's just get fresh eyes on rocks and you'll be able to make new interpretations. But it was mapped as the boundary between crystalline rocks to the north and then metamorphic rocks to the south. And so we thought we were looking at metamorphic rocks. I mentioned before there's been lots of glacial retreat. Believe me, this is all going to tie together. But if you look at the left, you're going to have to eyeball it because I don't have a pointer. But notice that glacier is this one continuous ice mass. And it's retreated, so there are now actually a few lobes, and it's left behind bedrock that people didn't see before. Now it's there at the surface. And so we found a bunch of funky looking rocks. I blame no one for thinking that these were metamorphic because, I don't know, they're really altered and green. But we found pillow basalts, definitely not a metamorphic rock, really nicely preserved. And since we were under the impression we were in the mid-crust, we're like, this is really weird, and came up with all pillow of reasons why there might be basalts here. It turns out, and there's chert as well, which is also definitely not a metamorphic rock. It's an oceanic sediment. And we did some chemistry on it, found out there within plate ocean island basalts and some mid-ocean ridge basalt. And basically what we were looking at was melange. This is basically my favorite definition of what melange is: a big sloppy geologic unit that includes a bunch of stuff and serpentinite as well. And basically what I'll kind of, I guess, give the takeaway is that oceanic crust was getting scraped as it was being shoved down this subduction zone. So just like whatever's on the oceanic crust ends up in here. So I mentioned that we just kind of moved the location of that Border Ranges Fault based on a new understanding of the rocks in the area. So on the geologic map on the right, what was previously mapped as metamorphics, we reinterpreted then as chunks of preserved, oceanic crust and sediments. So it looks like this. You've got generation of mid-ocean ridge basalt at the ridge. The ocean is studded with seamounts, some of which have pillow basalt on them, and all of that just kind of gets shaved off as it gets shoved down the subduction zone. And that's the accretionary prism of the volcanic arc that dated to hundreds of millions of years ago. Okay, so this is like a really fast history of that accretionary complex. You've got part of it, which is the McHugh complex, which is all kinds of volcaniclastic sediments, and including those cherts and all the oceanic crust material. And then smacked in behind that is something called the Valdez group, which is flysch, which looks a lot different, but there's some contact between them, which is a fault. Okay, so I swear this is the end. Oh, and in between there's a few tens of millions of years of history that I skipped. Rapid uplift in the area we got from thermobarometry. There were several episodes of accretionary and erosive activity along the southern Alaska margin. So that graph on the left is really just saying, if you look at the top 200 million years ago, there's accretion, then erosion, accretion, lack of accretion, erosion. That's just to say that the subduction zone went from preserving sediments to not preserving sediments over 100+ million years. And then it all ended basically around 60 million years ago. It's capped by a conglomerate that's deformed only at its base. And so here, summary of key events in southern Alaska. I heard the bell go off, so I'll just leave you to read them. Thank you.
Okay, I believe we get a little bit of time for questions here. I can kick us off if needed. I mean, the question of the day, right, for this session would be, what are the tectonic questions, or let's call it the tectonic unknowns that stand in the way of better assessing geologic hydrogen? Let me be more blunt. What research is needed?
Top one, yes. Francisco. Yeah, do you want the microphone?
Yeah, go for it.
I don't know if this is on or not,
It
but
is.
okay, great. Yeah, absolutely. That top one, that's exactly right. Western California. And actually, I did my graduate work in the Sierra Nevada and a little bit to the west, but that's the Franciscan Formation, exactly.
Do we want to march down these? How would you like to proceed? Or how about this? I'm looking at our speakers here. If something jumps out to you as a relevant question, something you want to jump on, do it. I think these are working.
Not sure about, oh yes, it is. Great, okay. Yeah, I know this one's a little, I'll just hold it, thanks. Yeah, the top question's a really interesting one. I've been thinking about that a lot lately. And it just went away. I think I remember what it was. It was, yeah, there we go. How do we translate information from mantle serpentinization at depth to stimulated geohydrogen production shallower? And I don't think I can answer that question, but I think it's a really good, important question. And I am an experimental petrologist, and I have in my deep dark past some experience with high pressure hydrous minerals and their structures. And I know that people are getting at this question experimentally these days. I think the timescale issue that came up earlier is a really important question, though, and catalyzing that reaction. It seems like there's some ways to do it, but I'm hoping that people doing research on this can keep that front and center, because I think if we can stimulate it at much more amenable depths and temperatures, that'll be a really good addition to this. Then we might not have to go look for it in very remote places. We might be able to find a more accessible place and then actually stimulate hydrogen production.
Want to scroll us down? I don't know who's driving. I'll scroll us down for a moment there. There you go.
To answer, do we get earthquakes from subducting slab cracking during serpentinization? We do absolutely get earthquakes from the subducting slab cracking. I do not know if that is during serpentinization or not, because serpentinization involves like a lot of fluid fluxing through, right?
A plus 40% volume change. So the volume of rock expands by 40%, and this is accompanied with a significant increase in the positive buoyancy of that body of rock. So it also influences subduction zone dynamics.
The creation of serpentine absolutely drives earthquake activity in the slab. So we're just kind of, if something jumps out at you here, panel, go for it. And in the room, if you got questions you want us, just put your hand up and I will make sure that we get you inserted here.
I did see the question on faults like the border ranges fault penetrate the crust. I think generally the answer is yes. There's been a really good seismic studies across Alaska as part of the EarthScope project. And what we do see is a lot of these terrain bounding faults are imaged really well at depth. Do they penetrate the entire crust? I don't know the answer to that, but I think Bob probably knows. Is that a yes? Yeah.
Elizabeth, can you reiterate that for?
So Denali Fault absolutely penetrates the crust. Border Ranges Fault most likely does, given that it was a former subduction zone. And I just remember having seen in the past talks about some of these other terrain bounding faults that they are imaged pretty deep down. And some of the ones that don't break the surface, like the boundary between the peninsular terrain and the rest of North America to the north, it's not exposed at the surface, but it is seen at depth through seismic studies.
Yes, we got a question here. And Marisa, can you just distill that question for people who are listening on the mic?
Yeah. So when you're thinking about I think the fundamental question that you're asking is how does porous versus channelized fluid flow and the nature of the fluid, either an aqueous fluid or a supercritical fluid, change the serpentinization process? And I think to sort of think about that, we have to recognize the processes that are generating the geologic hydrogen, right? It's not just serpentinization, period, done. It is the ferrous to ferric oxidization of iron that is actually generating the hydrogen gas by cutting the water molecules in half. And that is something that is less dependent on the pressures and temperatures of metamorphism or serpentinization. I will point out also that serpentinization does occur in the shallow subsurface in channelized faulting environments. And as far as we can tell, the mass balance doesn't change significantly, depending on whether or not it's an aqueous fluid or supercritical fluid moving around grain boundaries or channelized fluid flow. Where that's going to become important in terms of thinking about how much hydrogen gas we're generating is going to be in terms of thinking about our water-rock ratio, where it is difficult to get really high water-rock ratios in more channelized systems as opposed to more porous systems. I hope so.
Other questions around the room? Yeah, we've got one and then two. Okay. Sir.
Absolutely.
In a lot of ways, that describes the nature of our state. Or we're blessed and challenged, I guess you could say that way.
Next up, yeah.
I can't speak for all of them. I do know that recently researchers at UAF contacted me about anomalous methane seeps between the foothills fold and thrust belt and Fairbanks, so 40 or 50 miles south of here. Brand new faults that have never been identified, that are real and look geomorphically significant to have had a few significant earthquakes before human modern times. But they've got a lot of methane associated with them. I don't know how deep that methane is or how that applies elsewhere, but certainly I think some do, and that may be one path to identify some of those.
And some studies of like the Denali fault show. Yes.
I do believe that there's been animal methane sampled along the Denali fault. I don't, so that would have been stuff Jeff Benowitz done. I don't think I've seen any published.
Anyone? Do we have time for one more? All right, one more question. Sorry, I see two hands.
Subduction is happening in the near ocean. Is it easier to measure possibly gas seeps there? And are we seeing any? I mean, it may be easier to start it in the water than the air.
I would lean towards no, given the depth of that trench offshore, but
Yeah, I'm actually going to go see if I can find information on that, but it's challenging because the trench that forms when you have this sort of plate interface, its subduction is pretty deep, and actually Bernie is probably the better one to answer oceanography questions and marine science questions here. But my knowledge is that our oceans around the like Aleutian Island arc are pretty unexplored. More work really needs to be done, but so I couldn't tell you if there's active gas seeps coming out in the ocean. I don't know. Do you know, Bernie? There are any? No, I should hand Bernie the mic.
Okay.
Active gas seeps coming out along the Aleutian Islands submarine that you would see. Yeah. Yeah. Yeah.
Do the serpentine mud volcanoes? Do the serpentine mud volcanoes have?
Okay, on that note, I think we'll wrap up our session, give a hand to our panelists, and pass it back over here.
Well, it sounds like we have a lot of new questions. Be sure you write those down in Slido or on a 3x5 card and put it in the envelope on your table.
So I have a couple of announcements before we start the session, and one of which I've been meaning to say all day but haven't, and that is that there are several boxes of rocks in the back of the room over there that are from ultramafic systems around the state. There's a box of core from the Duke Island complex, which is in southeast Alaska, and I believe was part of the research that we heard about earlier today. There's also a box of core from Union Bay back there, and some core samples from, I think it's the Kenai ultramafic complex. So these are samples of ultramafic rocks that are either unserpentinized or completely serpentinized. And they all came from the Alaska Geologic Materials Center in Anchorage, which, if any of you don't know about, has hundreds of thousands of feet of core from all across our state. And it's a wonderful repository that you can visit, examine the core, do some sampling yourself. You can find out more about it from our next moderator, who's Dr. Melanie Worden, who's the state geologist and in whose tender care the Materials Center is. The other thing is, don't forget about Geoff's talk at the pub at 5:30 this afternoon, which is just downstairs down there. Another thing is the parking lot, the Nenana lot, which is across from the Student Rec Center. Apparently the pay kiosk wasn't working this morning, so if you parked in that parking lot and it wasn't working, there's a chance that you could get a ticket, I guess. And we're hopefully not, but we're working on that to see if there's a way we can resolve that potential issue. I guess if we alert them to the fact it's not working, maybe they give everyone a ticket. And then finally, just a safety thing. As we leave here today, I'm sure you found out it's really kind of slippery out there. There's fresh snow on top of the ice, and we don't want anybody to have any slips, trips, or falls, because it hurts when you land on ice. Okay, so our last session today is another one on Alaska geology, and to moderate that session, we have Dr. Melanie Worden, who is the current state geologist and director of the Alaska Division of Geological and Geophysical Surveys. And their office is just down the hill from us here. So if you have any questions for Melanie or her staff, you can find them down there. Melanie received her PhD in Brooks Range base metal deposits from UAF. So she's got a long history in economic geology, and has been with DGGS for quite a while, I think over 25 years. Is that right, Melanie? And has conducted all sorts of geologic investigations across the state, and her knowledge of the geology and mineral resources of our state is really second to none. So, Melanie.
Thanks, Steve. Okay, one quick note. We will have 2 speakers today, not 3. Sean Regan is a professor here at the university, and he sends his apologies. He had to leave for emergency situation out of state this weekend. So I hope you have a chance to meet him at some future conference here. And so we do have 2 speakers here. One's going to be virtual, and the other one here is in person. And so I will start with Aaron Todd. He received his PhD from the University of California, Santa Cruz with his advisor, Jim Gill. And he did a postdoc fellowship at the University of Munster, Germany with an advisor, Andreas Sfraga. For both of his degrees, his research focused was the geochemistry and isotope systematics of oceanic basalts. Aaron is a research geologist at the U.S. Geological Survey's Alaska Science Center in Anchorage, and he specializes in igneous petrology. He is currently project chief of a research effort interpreting the styles of magmatism represented by ophiolitic rocks in Alaska, and he is also supporting igneous geochemistry tasks in other projects. And one of these includes Doug Kreiner's Earth MRI Kuskokwim project in Southwest Alaska. So welcome, Aaron. Barb indicated we have time for a question, and it'll either come up on the screen here. Yep.
So I will unshare.
Okay, how far into the subsurface do you expect surface data to be useful in hydrogen exploration? Aaron, you mentioned that there's some mafic, ultramafic rocks that are flat versus those that dip into the ground.
Yeah, well, I'm not sure I'm the best to answer this particular question, but I think it depends on whether or not you're looking for stored hydrogen or the potential to induce hydrogen. So these big bodies of olivine-dominated rock could be comparatively accessible for the latter. I think if you were trying to determine where to find the former, it seems you might want to look at these layered intrusives rather than the ophiolitic bodies. In which case you might be able to get into something where a natural trap seals. And I think there it depends on what the overlying geology is more than what the depth is.
Thanks. And one quick question here for Sue. Do you know what the temperature of the hydrogen generating replacement reaction is from arfvedsonite to adrine?
The best reference for this is the Salvia and Williams-Jones. Around in the vicinity of 200 to 300 degrees centigrade, it's pretty low temperature hydrothermal alteration conditions. And Truche and his co-authors, and he's in France, have done a lot of experiments with that. And so if you look up his work, it's TRUCIG, you can read about the various temperatures and pressures that they experimented with this reaction.
Okay. And just to refine the comments about smoky quartz, can you use it as an indicator for potential geologic hydrogen production?
No, well, I wouldn't say so. Mainly it's an indication that you have radiation damage, and that means you probably have uranium and thorium in the, not maybe even in the quartz, in the crystal lattice. So it's not, I think what you want to, my understanding from from the little amount of reading, I'm not an expert on this by any means, is that it's the hydrothermal alteration that is going to really tell you if you've had hydrogen generation from the oxidation of iron.
Okay, thanks. And last question for Aaron. Is the MagmaChem terrain buried under the Koyukuk Basin sediments, and any sense where other ultramafic rocks are under sedimentary basins?
I think the mapping suggests that the answer is maybe. There's a gentle dip associated with these things. But to my knowledge, the resolution of the geophysics in the area isn't robust enough to determine how much of that material and how magnetic it is at depth. So, yeah, to be determined. Let's hope that more geophysical surveys can be done to answer.
I'll agree, since we do them. Okay, well, thanks everybody.
Okay, now we're going to do the fishbowl part, and I'll explain. In a fishbowl sandwich, in a fishbowl, everybody can be a fish. Every one of you can be a fish. The fish are going to sit up here on the stage. So here's the following rules about fish bowls. You can only talk if you're sitting in one of these 4 chairs. Otherwise, we're listening. If you have something to say, come and sit in an empty chair. You don't have to wait for somebody else to quit talking. You can just come up and sit down while they're talking. If all the chairs are full and someone else new walks up, the person who's been sitting there longest should leave. It's only 4 people at a time. The topic of the fishbowl is, what is the most compelling argument for the generation of significant geologic hydrogen in Alaska? And that should be in the books. Is it not in the books? On page 9 of the notebooks. Yep. What is the most compelling argument for the generation of significant geologic hydrogen in Alaska? If you have an answer already right now in your mind, please come up and share it with us. I should have asked somebody to come up first. Yes, come up. Yes. Yeah, come on up. Sit in a chair, grab a mic. Here, tell us your thoughts.
Ed Donaldson, Bureau of Ocean and Energy Management in Anchorage. I'm a relative novice to this compared to a lot of folks in the room, but just based on the presentations and what I know about serpentinization, which I always mispronounce, there is an awful lot of the minimum requirements of source rock heat. And the reality is you have the core geologic elements for serpentinization in this state. I mean, to me, that's just obvious, except that it's largely offshore. And so it occurs to me that considering offshore, never mind that I'm at the Bureau of Ocean and Energy Management, but I'm influenced by the presentation about these zones that would be beneath the subducting plate. The zone in the accretionary wedge is a lot harder to get to. That's my thought.
First test is, can you? Okay, you got 2 feds up here. I'm Doug Wicks from the Department of Energy, Advanced Research Projects Agency. I'd say the most compelling reason to do this is there's a high probability that it's here. It's a primary energy source. And if you do it right, you get it out of the ground. You don't have to refine it. You might have to polish it, but there are systems out there to use it. Expectations is it's going to be inexpensive, relatively inexpensive. You don't need any other infrastructure to build it. You don't need to build large amounts of renewable energy to electrolyze water. You don't need to move methane around and worry about CO2 emissions. If you want a clean economy and have it be within your state, I would fully recommend getting after it. I think it's a great opportunity up here, especially in your remote regions. We heard a lot about small intrusions coming in. If one of those are next to one of your remote villages or towns, I should say, I don't know, do you call them villages or towns? But then you don't have to airlift in diesel to do it, and it's a clean energy source.
Allegra Husfordshire from Stanford. I'm just going to say, because it's been found in dozens of countries worldwide and dozens of states in this country. So yesterday announced in Algeria, Friday, Morocco, Korea was announced last week, West Virginia was announced last week. So because it's probably there is my provocative answer.
Simon Harrison, Alaska Marine Power in Anchorage. The question was, what is the most compelling argument for generation of significant hydrogen in Alaska? And my simple answer to that is because it's needed to get us off the hydrocarbon out of the hydrocarbon age. We need to stop warming this planet, and this is a major reason to doing it. It isn't necessarily going to make us rich, but it's important for the livability of this planet, and we need to get on with it.
So I understand the question is, why is Alaska? So I understand the question is, why is Alaska favorable for hydrogen? Is that what it was?
Generation of significant geologic hydrogen in Alaska.
Argument for the generation. Oh, okay. So my thought is that the geology of Alaska has a history of steep and flat subduction and rifting. All of these generate subduction. But it's especially important to recognize that Alaska has a reduced crust. That's why you have so much gold, because gold gets stuck in the magnetite in oxidized plutons, but you have ilmenite plutons and you have gold in the hydrous phase. So Alaska is reduced in its chemistry, and that is critical to get hydrogen to the surface. Even if, no matter how it's generated, you have to have a reduced crust. And the other thing is you've got history of accretion of oceanic crust, and especially lithospheric mantle, which is always serpentinized. It doesn't just start right at the trench. It's serpentinized as soon as it gets off the ridge. And it's serpentinized especially along the fracture zones. And I think the best argument is that you have a large geologic database which needs to be compiled and looked at from the perspective of what kind of a terrain do you get serpentinite in? I mean, it needs to be analyzed to determine that. So, and it's already there.
Be bold. Disagree.
We saw a lot of really good geology today, but what we didn't see, we saw surface outcrop data primarily. And if you look under those shallow sedimentary basins, there's a lot more of it, a lot more potential for having the right rocks present. Again, many of these basins, we have very little seismic or well data. We can't define these basins well. We have gravity magnetics and some old seismic, but we have a map that would look a lot different if we stripped off the covers of the surface, where surface geology and miners go. So the fact that we have as much on the surface, and we know we have this complex subduction history, as Monte alluded to. You look at the evolution all the way to the Brooks Range of the subduction zones and the timing. We have more than 100 million years of subduction data basically going on with a basin that we really haven't clearly defined in terms of the source rocks. And within those sedimentary basins, we don't understand the trapping mechanisms. It's a lot of risk, but there are a lot of opportunities for structural and potentially capillary pressure traps. The other thing I think that could really be important that we do not at all understand is the role of the hydrological system, the water interface between the surface, but we have permafrost. So we actually have thousands of years of frozen ground to deal with, which eliminated the surface water interface to the lower water. And that might be significant as well. So we might have unique opportunity in the sense of where we have more continuous permafrost. It may not make a difference, but we don't know. So to me, it's really the fact that underlying these sedimentary basins, we have a tremendous potential that we have not yet mapped.
Barb, thanks for this question. So yes, my name is Kathy Giesel. I'm a born and raised Fairbanks girl, a territorial kid. I'm a nurse practitioner. I'm also an Alaska State Senator. So when I hear this question, the most compelling argument to me, overriding argument would be for security. So what does that mean? I mean energy security, diversify Alaska's energy source. Right now we depend on hydrocarbons, and as any of you Alaskans know, Cook Inlet is running out of natural gas, at least natural gas behind pipe. We've got stranded gas on the North Slope. Yes, we have oil, but that's the second security, environmental security. You've heard discussion about getting off hydrocarbons and reducing the global warming issues. That's important. This is a wonderful source of clean energy. Yes, we have hydropower, we have wind, we have solar, but this is yet another diverse form of environmentally safe energy. Certainly economic security. Right now, Alaska is losing population. We've been losing population for 11 years. The age group that we're losing is age 18 to 64, our working age population. Families are leaving. Jobs are unfilled. Last night, we had a huge snowfall in Anchorage. When I left my home at 5 a.m. this morning to fly here, there wasn't a single snowplow in sight. The roads had not been plowed yet. We have a shortage of snowplow operators, heavy equipment operators, mechanics, diesel mechanics. We need to bring that population back. How do we do that? By diversifying the job opportunities here. Geologic hydrogen, that's a great, that would create great jobs, high-paying jobs. It would challenge young people to stay here. It also would induce us to continue to fund this university, which is where we're meeting today, an important place. But it also would have social impact. And that, again, is returning to our schools and the education opportunities here. So when I, as a lifelong, born and raised territorial kid, when you ask me the most compelling argument for a new form of energy, it's social reasons, economic reasons, national security. This would help our nation continue to be an energy leader. Thanks, Barb.
Thanks, Senator Giesel. Thanks, Mark. My name is Meade Treadwell. I'm a former Lieutenant Governor of Alaska, former chair of the U.S. Arctic Research Commission, but don't hold that against me. I'm basically a businessman who invests in opportunities. My philosophy is invest in the inevitable if you can find the team to make the inevitable happen. I think here in this room, we've got a sense of what the inevitable is. Mark, you've made that very clear to me over a number of conversations. And how do we make the inevitable happen? One of the first things you do to make a new industry happen is to have a strong local market. In Alaska, we have the 4th largest air cargo port in the world. If there's, and we've got plenty of CO2 to collect, many different places to mix with hydrogen to make sustainable aviation fuel. That might be a strong local market to begin with. We have minerals that are shipped outside for refining right now, and a global market that's looking for cleaner minerals, less carbon intensive minerals. In fact, an Alaskan I know who built 2 Tesla plants is now building a steel plant, a clean steel plant, a green steel plant in Sweden. The other thing I'll just say is that we are already in the hydrogen business, in the natural gas business, whether it's our attempts to export North Slope natural gas or our use of natural gas and our pioneering export of LNG into Asia. I just got an email from the former head of the International Energy Agency, who's going to give a presentation here in January about Alaska and Japan and how we should be working together on hydrogen. So they've bought into it. The head of the Japan Bank for International Commerce called us and said, we've looked at the United States. The only place we could bring CO2 back is Alaska and California significantly. So we're already in that part of the business now. Whether we start in the hydrogen business with direct shipping of hydrogen, if we found that, taking hydrogen out of natural gas with a few new catalytic processes I'll talk about on Thursday, or ship it as ammonia, we will be building that infrastructure for international markets as well. And we're actually pretty well poised today, even before, I'm listening to a bunch of scientists talk about, well, are we going to get it from rocks? Are we going to get it from subduction zones? Are we going to get it from natural reservoirs or reservoirs that have been collected? We don't know that yet. In fact, the places where we found it, we don't know that yet. But the fact is that we are in the gas handling business. We are in the gas production business. We know that we can make hydrogen and either re-inject the carbon or turn it into solids like graphite or carbon black now and have a zero, ultimately very close to a net zero carbon impact. We should be in the hydrogen business today with what we've got and tomorrow with what we find.
Hi, everybody. Steve Masterman, Geophysical Institute. I guess I want to come back to something Ed said about the rocks and just expand on that a little bit more. One of the things we've heard today is all the different ways that hydrogen is generated. And when you go down that list, all of those conditions are present in Alaska. We have a 2,000-mile long subduction zone, modern subduction zone, under the Southwest Alaska, the Aleutian Arc. We have paleosubduction zones, numerous paleosubduction zones across the state. We have uranium thorium deposits around the state. We have uranium thorium potassium bearing rocks that are going to produce hydrogen from radiolysis water as well as from alteration of the entrained minerals. And in many locations, or in some locations around the state, we have those rocks or can project those rocks onto sedimentary basins. And so we also have large-scale crustal structural features that could serve as conduits to bring deeply generated hydrogen up to the surface. So from my perspective, the rocks definitely speak to the compelling argument for hydrogen generation in our state. But one thing that stands out to me is that those rocks are distributed all across our state. Southeast Alaska, Southwest Alaska, Central, Northern, Northwest Alaska. So if hydrogen is being generated and if hydrogen resources are present, it could be a very distributed energy resource for the local communities in our state for for whom the cost of energy is literally prohibitive. And so for me, that's a very compelling argument as well.
Yago Lee from Carrasco Mines. So based on our group's research in recent years, we understand if we focus on the serpentinization or automathic rock alteration related hydrogen, there is an emerging understanding that the accumulation and source rock generation needs to have certain proximity in temporal and spatial distance. And we are looking at a very short time interval, possibly with high potential for retaining the hydrogen because of the spatial properties of hydrogen. And also there's a very limited spatial distance between the accumulation and the source rock. So the set of the presentations on geology in Alaska, you look at distribution of the automathic rocks and different ophiolites and also indicators that actually shows that has been a significant partial serpentinization happening in the recent geologic history. And all those zones and belts are tugged right against a lot of small basin environment. So that's actually based on general understanding. That's really what you need is the source rock and conditions that supports the alteration. And then also the short distance and the time allows the migration of the geologic hydrogen into the area in the sedimentary settings that could accumulate. So that set of presentations really providing the compelling argument in my mind that actually shows that geologically there should be huge potential for geologic hydrogen in Alaska. Thank you.
We have more time. No more opinions? All right. Thank you all for your perspectives. Now we come to the other side of the fishbowl sandwich. You've all been invited to be fish. Now you need to put your money where your mouth is. Think about your biggest takeaway from this session. Find someone you don't know and share your single biggest takeaway. So just think for a minute alone and then find someone you don't know. And also, where's Elena? I think this is a question in the Slido app about the single biggest takeaway. Elena? Oh, I'll find her. Have your 1 minute thinking. What's your biggest takeaway? I'll be right back. All right, find someone, have a conversation, and then enter it into the Slido. What's your single biggest takeaway from this session? And we will stop at 10 minutes to 5. At 4:50, we will stop talking. All right, wrap up your discussions now. And please enter something into the Slido. We only have 3 entries right now, and there's almost 100 people in here. So I'd like to have everybody submit what's your biggest takeaway from today. Okay, can I have your attention, please? We'd like to get out of here on time tonight. I'm sure you would too. Please stop what you're doing now talking. Enter something into the Slido. We really would like to know what your biggest takeaway is from today. Everyone should enter one. I will too. And then we have just a couple more announcements, and we have a feedback form. So we'll do, if you're done entering your Slido, you'll find a half sheet of paper on your table that says feedback form. And we'd like you to fill that out and put it in the out envelope. This will help us to correct things that we may have done, you know, maybe we could do it better tomorrow. Also, we'll give feedback to the organizers on other things that may be important to you. After they do the feedback form. Yeah, yeah, closing. Okay. Do your form. I'm so glad you're here. You're in.
If you have a gong or a glass, because sometimes we're starting back fingers asking their sounds,
They can't hear it.
They can't hear it, but
Yeah.
a gong or a
Where would I
glass-
get one?
Glass with a spoon.
Okay.
There.
Okay. Got this thing. I have not used yet.
Give it that glass with a bottle with a
Oh.
spoon.
Okay.
That's really large.
Loud. Okay.
Loud.
Loud. Got it. Please fill out your feedback forms and put them in the out envelope.
Well, everybody, I think that's after you put your forms in the little envelope there, I think that basically concludes today. I just have a couple of closing announcements. If you wouldn't mind clearing off the trash off your tables, and if the bins are full, put it on the back tables over there. Don't forget that Jeff Ellis's talk is down in the pub at 5:30. So half an hour from now, Jeff will be on deck. And I think the pub is open, so we can go down there and have an early beverage. And then finally, if any of you are here alone and wish to find a friend to go have dinner with, you can meet at the message board and team up and find a friend to go have dinner in town, I guess. Or you can do the same after Jeff's presentation in the basement. So thank you all for your active participation today, and we'll see you downstairs or tomorrow in the morning.